Hello there, and welcome back to the Science Sleepy Minds, where tonight, with the blanket tucked just right and the fan already humming its soft little lullaby, you are going to slip into a very heavy spacesuit, step through an airlock, and set one slightly shaky boot onto the cold, rust-coloured dust of another planet. You are one of the first humans on Mars. The sky above you is the colour of weak tea. The sun is smaller than you remember, and paler, and faintly apologetic about it. Your breath fogs inside the helmet. The ship that brought you here sits a short walk away, gleaming in the low sunlight, looking for all the world like a ride home. And this is the part that's going to slowly break your heart over the next 40-some minutes. That ship is not a ride home. Nothing on this rock is a ride home. You have stepped through a one-way door, and you did it voluntarily and cheerfully and with paperwork. You probably won't survive this, not in the dramatic crushed by a meteorite sense, but in the gentler, much more certain sense that your skeleton, your heart, your immune system, and your Earth-adapted biology will all be slowly rearranged by a planet that does not care who you are. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while the helmet defogs, drop a comment telling me where you're listening from and what time it is for you, because I love picturing all of you spread across every time zone, eyes half closed, listening to me gently explain how you're about to die of physics. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You look up at the tea-coloured sky. The ship, that sleek, confident ship, sits like a monument to a journey you will never repeat. Someone on the crew turns to you and says something muffled through the radio, and you nod because what they have said is obvious. The landing was the easy part, the leaving was the easy part, getting here was the easy part. The going back, it turns out, is the hard part. The going back is the part we don't talk about in the shiny brochures. Going back is the reason tonight's story exists. Because here is the strange, quiet secret at the centre of every serious Mars mission plan. There is no convenient return. There is no Mars taxi stand. There is no, and then a ship comes to take us home clause. At least not one that holds up to careful reading. To physically bring a human body off the surface of Mars through its atmosphere and back across tens of millions of kilometers of vacuum requires machinery, fuel, time, and political will of a kind that the first missions will almost certainly not have. You might build a return ship, you might manufacture fuel on Mars, you might wait patiently for Earth to align with Mars just so. And yet, for reasons we will lovingly unpack over 20 sections tonight, the first humans who go to Mars are overwhelmingly likely to stay on Mars forever. Historians still argue whether that fate was obvious from the beginning, or whether we really meant all the cheerful PR promises, but the honest engineers have been whispering it for decades. You feel the weight of that as you stand in the dust. It is a strange, soft weight, because Mars's gravity is only about 38% of Earth's. Your body feels light and airy. A backpack that weighs 15 kilograms on Earth feels like about 6 kilograms here. You could, if you were in a silly mood, do small jumps with comically long hang time, like those old Apollo moon clips, except slightly more grown up and slightly less buoyant. Your colleagues are already doing it, a little, because everybody does it when they first arrive. The psychologists back on Earth probably predicted this. They probably have it in the mission logs as expected light jumping behaviour phase 1. And you laugh gently inside your helmet, and then you look back at the ship and the laugh quiets. Because here is what you're going to learn over the course of tonight's long, patient tour. Every piece of the puzzle, the physics of rockets, the biology of bone, the economics of rescue, the politics of priorities, the geometry of orbits, the chemistry of rocket fuel, the psychological toll of isolation, the stubborn dust that gets everywhere. Every one of them points in the same sleepy direction. They all very politely gesture you towards staying. Not one of them demands it. But every one of them nudges, and when you stack them together, the nudges become a firm, gentle, cosmic hand on your shoulder, whispering, "You're staying, buddy. You're a Martian now." The quirky fringe fact to carry into the night is that this was not always the plan. Some of the earliest mission concepts for human Mars exploration assumed a flags and footprints structure in which astronauts would arrive, plant symbols, collect samples, and return in triumph. It was only as engineers looked harder at the fuel, the radiation, the bones, and the budgets that the one-way scenario started becoming the default assumption in many proposals. One famous concept, Mars to stay, was pushed seriously by several aerospace engineers in the 2000s, and it essentially argued that the first mission should not pretend to bring people home. It should just commit, send them, keep them, support them. That plan was controversial, but it has quietly shaped a lot of what serious engineers now say to each other when no cameras are rolling. You breathe once, slowly, and you start to walk toward the habitat module. The dust puffs under each footstep in tiny lazy clouds. The ship looms behind you, metallic and optimistic. You try not to look at it, because looking at it brings a little ache you cannot quite name. Remember that ache, because it will come back. For tonight though, let's take it very, very slow. Let's walk through, section by section, exactly why that ship is never going to take you back to Earth. You start with the simplest, cruelest fact of the whole story, the distance. Because before any rocket engine, before any bone loss, before any dust storm, before any bureaucratic budget cut, there is the raw, mathematical, unreasonable distance between Earth and Mars. And this number is the quiet villain of every Mars mission plan ever drafted. You don't fight this number. You negotiate with it. You lose most of the negotiations. Earth and Mars are neighbours in the loosest possible sense of the word. They are both rocky planets in the inner solar system. They both get warmed by the same small yellow sun. They have much more in common, physically, than either of them has with Jupiter or Saturn. On paper, they are the two siblings of the inner rocky family, along with Venus and Mercury. In practice, Earth and Mars are separated by a gulf that is difficult to hold in the human mind without a steady breath. Let's try anyway. When Earth and Mars are at their closest, which happens once every 26 months or so, they are roughly 54 million kilometers apart. That is already a lot. Light, the fastest thing in the universe, takes about 3 minutes to cross that distance. When the two planets are at their farthest, on opposite sides of the Sun, they're about 401 million kilometers apart. At that range, light takes over 20 minutes to travel. The average separation is around 225 million kilometers. 225 million. A distance so large that every comfortable analogy starts to fail. Here is a mainstream fact to roll over in your sleepy mind. If you built a highway between Earth and Mars, paved and straight, and you drove down it at a steady 100 kilometers per hour without stopping for fuel, food, or bathroom breaks, which, yes, physics would not allow, but let's play, it would take you approximately 257 years to reach Mars. 257 years, at least 4 human lifetimes. Enough time for an entire country to rise, fall, and be studied in college classes. You would die. Your grandchildren would die. Your great-great-great-grandchildren would be the first of your line to see that distant little red planet appear in the windshield. This is a joke, of course, because nobody's driving to Mars. But the reason we're laughing is that the distance is honestly, genuinely, that ridiculous. Light joke for tonight. Imagine your weather app on your phone and imagine it trying to give you a forecast for Mars. The weather data would be at best about 3 minutes old, and at worst about 20 minutes old. By the time your phone said light winds at Jezero Crater, the Martian weather would already have moved on. And honestly, on a bad day, your Earth weather app can't even give you accurate data for tomorrow in your own city, so your Mars weather app's excuse is weirdly defensible. Now rockets move faster than highway cars, a lot faster. Modern spacecraft heading to Mars typically travel between about 50,000 and 90,000 kilometers per hour, depending on the mission profile. Even at those speeds, a one-way trip to Mars typically takes between 6 and 9 months. 6 to 9 months. For the astronauts, that means about 200 days in a metal tube, floating in weightlessness, eating food that was vacuum-sealed at home many months earlier, watching Earth slowly shrink behind them, and Mars slowly grow ahead of them. There is no pull over and rest on this trip. There is no turn around, I forgot my phone charger. Once the burn is done and the spacecraft is committed to the transfer orbit, the crew is on their way, and they will be on their way for months. Here is the quirky fringe tidbit for tonight. The specific kind of orbit most Mars missions use is called a Hohmann transfer orbit. It is a clever, fuel-efficient curve around the Sun that lets you leave Earth when Earth is at one point in its orbit, and arrive at Mars when Mars is at another point in its orbit, much later. The orbit was worked out in 1925 by a German engineer named Walter Hohmann, who published it in a book called Die Erreichbarkeit der Himmelskörper, which translates roughly to The Attainability of Celestial Bodies. A book title so dry it could double as a sleep aid on its own. Historians still argue over how much credit Hohmann personally deserves versus earlier Russian and French theorists who had similar ideas, but the name stuck, and nearly every interplanetary mission since has used some variant of his basic design. What does all this distance mean for the first humans on Mars? It means the trip is long. It means rescue is slow. It means returning is hard. It means the Earth they left is not going to be the Earth they find if they come back, which, spoiler, they almost certainly will not. In the 6 to 9 months they are travelling, a lot can happen. Governments change, funding shifts, political priorities move, and the astronauts themselves are physically changing in ways we are about to describe in painful detail over the next several sections. You sit with that image for a moment. Earth behind them, a blue-white marble. Mars ahead, a rusty pinprick. No shortcuts, no off-ramps, no truck stops. Just the tin can, the vacuum, and the patient slide of orbital mechanics. The spacecraft is moving, sure, but from inside nothing seems to move. You're essentially sitting still in a small room while the universe rearranges around you. The psychological effect of that is, we are learning, not small. We'll talk more about it later. A second light joke tonight. The first humans on Mars are essentially signing up for the world's worst road trip and the world's best road trip simultaneously. The worst, because there are no snacks, no gas stations, no scenic overlooks, and no music that isn't a few gigabytes of preloaded audio. The best, because, well, Mars. You arrive at Mars. No Earth road trip can match that one arrival. It's just that the journey is 6 to 9 months of nausea-adjacent floating, and the arrival is followed by a life you cannot leave. Historians still argue whether the journey time will come down dramatically in the coming decades. Some engineers, especially those associated with nuclear thermal propulsion and fusion propulsion concepts, argue that future spacecraft could cut the Mars trip to just a few months, or even a few weeks. Others point out that we have been predicting imminent revolutionary propulsion for about 70 years now, and it has stubbornly refused to arrive. For the first crewed missions, we're almost certainly using chemical rockets and 6 to 9 month transfers. That is the baseline reality. Faster trips are a future promise, and tonight we're concerned with the present. You settle deeper into the pillow as we approach one of the strangest, most beautiful and most tyrannical facts about travelling to Mars: the launch window. Because going to Mars is not like catching a bus. You cannot just leave on Tuesday because Tuesday is convenient. Mars and Earth are both spinning around the Sun in their own orbits at their own speeds, and they only line up in a useful configuration every 26 months. If you miss your window, you're waiting another 26 months. That is a little over 2 years. That is 2 entire years of looking at the sky and knowing the universe has told you, politely, no. Here is the physics. Earth orbits the Sun once every 365 days, approximately, hence our year. Mars orbits the Sun once every 687 days, approximately, because it is farther out and moves slower along its longer path. The two planets are therefore moving at different paces around the same track. Occasionally, they come close to each other. Then they drift apart. Then they come close again. The average time between useful close approaches is about 780 days, or roughly 26 months, which astronomers call the synodic period of Mars. The synodic period is what sets the launch schedule. To send a spacecraft from Earth to Mars efficiently, you need to fire it off when Earth is at just the right spot in its orbit, such that months later it arrives at Mars's orbit at just the time when Mars is also at that spot. Think of it like throwing a tennis ball at a target that is slowly moving, but throwing from a platform that is also moving, in a way that means you have to lead your shot across an enormous 3-dimensional track. And if your aim is off by even a tiny fraction, you miss by thousands of kilometres. This is, charmingly, an entirely solvable problem with modern computers, but it is only solvable during a narrow window. A typical Mars launch window lasts about 3 to 4 weeks. That is it. You have a few weeks to get your rocket onto the pad, fueled, checked, crewed, cleared and launched. Miss it, and your whole mission slides by 26 months. In human terms, that is a long, long slip. In budget terms, it can be fatal. In career terms, it can consume a significant portion of a person's working life. Here is a mainstream fact for the night. Every major Mars mission you have ever heard of, Viking, Mars Pathfinder, Mars Exploration Rovers, Mars Reconnaissance Orbiter, Curiosity, Perseverance, Tianwen-1, the Hope Orbiter, all of them launched during their respective windows. You can look at a chart of Mars mission launch dates, and you will see the clean, repeating cadence: 2003, 2005, 2007, 2011, 2013, 2016, 2018, 2020, 2022, and so on. Each blob of missions falls within a few weeks of each other, because they all had to catch the same cosmic door as it swung briefly open. Historians still argue whether Earth's space agencies would have sent more missions to Mars if the windows were wider, but either way, the rhythm is the rhythm, and nobody negotiates with it. Now let's layer this onto human Mars missions. To send humans to Mars, you use a launch window. Fine. They travel for 6 to 9 months. They arrive at Mars. Now what? They cannot just turn around and come back immediately. They have to wait for the next useful alignment for a return trip. And here is where it gets cruelly comedic. The next favourable launch window for a return from Mars, after the arrival window, is usually at least a year and a half later, sometimes close to 2 years. This means that even in the best case, a full return mission, with all the fuel, supplies and hardware already in place, the astronauts are on Mars for at least 500 days. That is nearly a year and a half just sitting on Mars waiting for the universe to realign. Then 9 more months in transit. Then Earth. Light joke time. Going to Mars is essentially agreeing to the world's most extreme travel insurance exclusion clause. Please note, your return flight will be scheduled according to planetary alignment. In the event of an emergency, please still consult the planetary alignment. In the event of a death in the family, please still consult the planetary alignment. Planetary alignment cannot be rescheduled. Planetary alignment has no customer service line. Please do not call us about planetary alignment. It will happen when it happens. The quirky fringe tidbit for tonight is that not all launch windows to Mars are equally good. Because Mars's orbit is somewhat elliptical, some windows are significantly more efficient than others. The 2003 window was especially notable because Mars was unusually close to Earth, closer than it had been in about 60,000 years. That's not a typo, 60,000. Astronomers made a huge deal out of it. The 2018 window was also relatively good. The 2033 window is already being anticipated as a prime target for potential crewed missions. So when serious engineers talk about when humans will first go to Mars, they are not throwing out dates randomly. They're consulting a cosmic schedule that has its own preferences, and dates like 2033, 2035 or 2037 come up repeatedly because those are when the door is most open. Historians still argue whether a first crewed mission might attempt a short-stay profile, where astronauts stay on Mars for only a month or two before heading back, or a long-stay profile where they stay for 500 days or more. Each profile has advantages. Short-stay missions minimize the time spent in Mars's radiation and dust environment, but require more propulsive delta-V and therefore more fuel. Long-stay missions sit on Mars waiting for better alignment, requiring less fuel but more surface life support. Most serious mission planners currently favour long-stay profiles because ironically they're cheaper, even though they keep the astronauts in harm's way for longer. And here is the second light joke of the section. If you think your vacation's return flight was inconvenient because it had a 4-hour layover in Frankfurt, just imagine your return flight from Mars. Layover duration, 17 months. Seat assignment, none. Please bring your own seat. Cushioned preferred. Amenities, a planet. Reading material, the planet. Wi-Fi, no, but there is a 20-minute round-trip delay to Earth, so please use it wisely. So now you have the second great one-wayness of Mars travel. The distance is brutal. The launch windows are narrow and rare. And if everything goes perfectly, fuel, hardware, politics, health, the earliest astronauts still have to commit to at least 2.5 years away from Earth, with no option to come back early if anything changes. For most of them, we are about to argue that window homes simply will not appear. Now we get into the beautiful, devastating, almost religious cruelty at the heart of spaceflight, the rocket equation. This is the piece of mathematics that every aerospace engineer has tattooed, metaphorically, if not physically, onto their soul. It is the equation that makes going anywhere in space hard. It is the equation that makes going to Mars enormously hard. And it is the equation that makes coming back from Mars, in a meaningful sense, almost impossibly hard. Tonight, in your sleepy state, you do not need to understand the math. You just need to understand what it whispers. And what it whispers is, every gram matters, and it matters exponentially. Here is the basic story told gently. To leave a planet, you need thrust. Thrust comes from burning rocket fuel. Burning rocket fuel means carrying rocket fuel with you when you launch. Carrying rocket fuel means the rocket itself is heavier, which means you need more thrust, which means more fuel, which means the rocket is even heavier. This feedback loop is the tyranny of the rocket equation. The amount of fuel you need grows not linearly but exponentially with how much speed you need to pick up. So small increases in mission requirements translate into large increases in fuel. The Russian rocket pioneer Konstantin Tsiolkovsky worked out the basic equation in 1903, which he reportedly kept scribbled on notebooks and envelopes. It relates the change in a rocket's speed to the exhaust velocity of its fuel and the ratio of its initial to final mass. You do not need the exact equation tonight. Historians still argue over whether Tsiolkovsky was the first to write it down, or whether earlier theorists had similar formulations, but either way, the equation is his name's legacy, and every launch on Earth is a tribute to it. Here is the practical consequence. If you want to launch a small crude capsule from Earth to low Earth orbit, you need a rocket that is mostly fuel by mass. About 90% of the weight of a typical launch vehicle on the pad is propellant. 90%. The Saturn V rocket, which took astronauts to the moon, weighed about 3,000 tons at liftoff, and most of that was fuel. The capsule that actually returned to Earth weighed about 5 tons. 5 out of 3,000. The proportions are ruthless. Now consider Mars. Landing a crewed vehicle on Mars requires carrying tons of hardware across hundreds of millions of kilometers, which requires more fuel, which requires bigger rockets. This part we can kind of solve. Modern heavy lift vehicles like the SpaceX Starship, NASA's SLS, and various Chinese designs can, in principle, loft the required mass into a Mars transfer orbit. The harder part is coming back. To come back from Mars, you need a separate rocket to launch from the Martian surface. That rocket needs enough fuel to escape Mars's gravity, and then to travel back across the vast interplanetary gulf. And that fuel, under the classical plan, has to be brought with you from Earth and landed on Mars first. If you try to bring enough fuel from Earth to both land everything, and then refuel for the return, the mass you need to launch from Earth explodes ridiculously. The return fuel tank becomes so heavy that your Earth rocket cannot lift it, or the Mars landing vehicle cannot land it, or both. The numbers break. Light joke for tonight. The rocket equation, in its soul, is essentially the mathematical version of trying to bring a carry-on suitcase to a party, and then realizing the suitcase has to contain a smaller suitcase full of the food you want to eat, which contains an even smaller suitcase for leftovers, and by the time you're packing, you realize you cannot fit the original suitcase into your car. Spaceflight is a packing problem. It is the world's worst packing problem. And the answer to the packing problem, almost every time, is take less. Leave things behind. Yes, even the crew maybe. So how do serious engineers plan to bring humans back from Mars? There are 3 broad options, and all 3 have problems. Option 1. Bring all the fuel from Earth. This, as we have just seen, is basically impossible with current rockets. The vehicle you would need to launch from Earth would have to be absurdly huge, and landing that much mass on Mars is itself a major unsolved problem. Option 2. Make fuel on Mars. This is called in situ resource utilization, or ISRU. You land empty fuel tanks on Mars, and then you use local resources, water ice, atmospheric carbon dioxide, to manufacture rocket propellant. This is clever, but it adds a huge amount of complexity and uncertainty. It is the subject of our next section, so we will come back to it. Option 3. Do not bring the crew back. This is the most radical option, and it is also, oddly, the most honest. If you accept that return is very hard, you can redesign the entire mission around it. You can send the astronauts with enough supplies to live on Mars indefinitely, and you can send more supplies on future missions. Over decades, you can build up a real colony. This is essentially the Mars to stay plan we mentioned earlier, and it is quietly the plan that many serious engineers prefer when they are having honest conversations. The quirky fringe tidbit for tonight is about one specific Mars return vehicle concept that has been seriously studied for decades. It is called the Mars Ascent Vehicle, or MAV. NASA and various partners have been designing MAVs since at least the 1990s, often in the context of sample return missions. A MAV large enough to carry a single astronaut from Mars to Mars orbit would be significantly bigger than any MAV that has ever flown or even been built for uncrewed sample return. Designs exist. None of them have been built. They live in PowerPoint slides and journal articles waiting for a budget that has not yet arrived. Historians still argue whether a crude MAV can be built within the next 2 decades on any realistic budget, and opinions vary sharply. A second light joke for the section. The first humans on Mars are essentially being given the world's strangest lunch bag. Here is your lunch. It contains the ingredients for a rocket engine. You will need to assemble the rocket engine, fuel it, test it, and use it to fly home. If you succeed, you may have lunch. If you fail, you will still have lunch, but you will be having it on Mars for the rest of your life. We hope you enjoy the lunch either way. So the rocket equation, in its quiet, ruthless way, essentially says, to come back from Mars, you either have to haul an enormous amount of fuel with you, or make fuel on Mars, or not come back. And in the next section, we are going to look at option 2 in detail, because the make fuel on Mars idea is both ingenious and, frankly, a little terrifying when you look at what it actually requires. So let's imagine you're one of the first humans on Mars, and you have signed up for the Make Your Own Fuel on Mars plan. The Mars Ascent vehicle is waiting for you. Empty. A tall silver creature standing in the dust, looking, if you squint, a little hopeful. Your job, over the course of your stay, is to fill its tanks with rocket fuel, not using deliveries from Earth, using the planet under your boots. Welcome to in situ resource utilization, a phrase so polite that it almost hides how dramatic an idea it really is. Here is the basic plan. Mars's thin atmosphere is about 95% carbon dioxide. Under Mars's surface, in vast amounts, there is frozen water, either as ice or as hydrated minerals. With enough energy, you can combine carbon dioxide from the atmosphere with hydrogen from the water to make methane and oxygen. Methane is a rocket fuel. Oxygen is the oxidizer that lets it burn. Together, they are a complete rocket propellant stack. You produce them, you liquefy them, you pump them into the MAV. Someday you climb aboard, press a button, and fly back to Mars orbit, where a larger Earth return vehicle is waiting. This is a beautiful idea. It is elegant. It is, in some abstract sense, the only way the return trip math actually works for a near-future crewed mission. It is also, to put it gently, an industrial process that normally happens in factories on Earth, surrounded by safety inspectors, redundant power grids, thick concrete walls, and entire departments of specialists. You're being asked to do it on another planet, in thin air, in the cold, with a crew of maybe 4 to 6 people, using solar or nuclear power, while simultaneously farming, maintaining a habitat, conducting science, repairing suits, and not dying. Historians still argue whether the first crewed missions should rely on ISRU for return fuel, or whether they should treat the first missions as one way and introduce ISRU gradually. Proponents of ISRU argue that it is the only path to affordable Mars return. Skeptics argue that depending on ISRU for crew survival is reckless, because if the fuel factory fails, the crew dies. And in a real sense, if it works perfectly, it works. If it fails even a little, if a valve sticks, if a solar panel gets dusty, if a pump seizes, the margin for error vanishes. Here's the mainstream fact. On board NASA's Perseverance rover, which landed on Mars in February 2021, there is a small instrument called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. MOXIE is roughly the size of a car battery, and its job is to demonstrate that oxygen can be made from Martian atmospheric carbon dioxide. It has done so multiple times, producing small amounts of oxygen from the thin air of Mars. It works. The proof of concept is real. It is quietly one of the most important demonstrations ever performed on Mars. Without MOXIE-like processes scaled up enormously, no crewed mission can realistically return. With them, maybe. Now let's talk about what scaled up enormously means. MOXIE produces about 6 to 10 grams of oxygen per hour. A crewed Mars return rocket would need many tons of oxygen and many tons of methane. To generate that amount of propellant over a 2-year window, you would need a facility that produces oxygen roughly 10,000 times faster than MOXIE. 10,000 times. That is not a minor upgrade. That is an industrial plant with compressors, heat exchangers, cryogenic storage tanks, electrical distribution systems, water handling systems, and redundant everything on Mars, on the surface of another planet, working reliably for 2 years before the crew ever tries to ignite the MAV's engines. Light joke for tonight. Making rocket fuel on Mars is a little like being handed a pile of sand, a bucket, a scroll of confusing instructions, and being told, build a microwave, you'll need it to reheat your soup. Oh, also, you're cold, and you will die if the microwave doesn't work, and you can't call anyone. Good luck. It's a very high-stakes kitchen project. The process itself has a lovely name. It is called the Sabatier reaction, after French chemist Paul Sabatier, who won the Nobel Prize in 1912 for his work on catalytic hydrogenation. The Sabatier reaction takes carbon dioxide and hydrogen, and, with a suitable catalyst and some heat, produces methane and water. The water is then split using electricity into hydrogen and oxygen. The hydrogen is looped back into the Sabatier reactor. The oxygen is stored, the methane is stored. Net result, from a pile of Martian air and water ice, a steady trickle of rocket propellant. Elegant on paper, brutal to implement. The quirky fringe tidbit is that this concept was popularized for Mars missions by a particular engineer, Robert Zubrin, in his influential book The Case for Mars, first published in 1996. Zubrin's Mars Direct architecture proposed that the ISRU plant would be sent to Mars before the crew and would manufacture the return propellant during the many months before the crew's arrival. Only once the fuel was confirmed in the tanks would the crew launch from Earth. This clever sequencing, send the factory first, then the people, dramatically reduced the risk and the fuel burden on the crewed launch. Many serious mission architectures since have borrowed elements of this idea, even if they have not adopted Zubrin's full plan. Historians still argue about how much of Zubrin's Mars Direct is practical and how much is enthusiastic storytelling, but his influence on modern Mars mission architecture is hard to overstate. Another light joke, the ISRU plant sitting on Mars is essentially the single most important appliance in human history. If it works, you get to come home. If it doesn't, you get to meet Mars more intimately than you ever planned. Imagine waking up every Martian morning, checking the status of your fuel plant first, before your coffee, before your oxygen check, before your weather report. The fuel plant status is the status of your future. Is it green? You might go home. Is it yellow? You might not. Is it red? Well, red is the Martian theme colour, and you will have plenty of time to reflect on that. Here is why even a working ISRU plant might not bring the first humans home. The plant is a single point of failure. If a dust storm damages it, and we'll discuss dust storms later, repair might be hard. If a compressor seizes, and they do, replacement parts are many months away. If the hydrogen feedstock runs low, and it can, production stalls. The plant needs power, reliably, around the clock for years. It needs maintenance that only a small team of highly trained people can perform in cumbersome spacesuits. And even if it works perfectly, it only solves part of the problem. The crew still has to be healthy enough to climb aboard the MAV, ignite it, survive the ascent, rendezvous with the Earth return vehicle, survive the return cruise, and survive Earth re-entry. And that, as the next several sections will show, is where human biology makes its own, quieter, very insistent case for staying. Remember the little Moxie, politely making its grams of oxygen per hour. Remember the ISRU plant, grand and fragile. Remember that even with both, the story does not yet bring anyone home. Now zoom out for a moment, away from the rockets, back to the journey itself. Because before any colonist ever gets to worry about ISRU or MAVs or Mars dust storms, they have to survive the trip. And the trip, it turns out, is quietly trying to kill them in ways that are invisible, silent, and measured in decimeter units. We're talking about radiation. Specifically, we're talking about the steady, relentless rain of energetic particles that crosses interplanetary space and pierces any spacecraft, any shield, any human body in its path. On Earth, you're protected from most of this radiation by two things. First, Earth's magnetic field, which deflects charged particles from the Sun and from deep space. Second, Earth's atmosphere, which absorbs the energy of particles that do get through. On the surface of Earth, at sea level, you receive a tiny dose of radiation from the natural background, about 2 to 3 millisieverts per year, depending on where you live. It is small. You do not feel it. It does not meaningfully threaten your health. In interplanetary space, neither the magnetic field nor the atmosphere is protecting you. You're just there, naked to the cosmos in a thin metal shell. Two sources of radiation dominate. The first is galactic cosmic rays, or GCRs, high-energy particles from distant supernovae, travelling near the speed of light, arriving constantly from every direction. The second is solar particle events, or SPEs, bursts of energetic particles released by solar flares and coronal mass ejections on the Sun. GCRs are steady and relentless. SPEs are occasional but can be intense. Together they constitute a hostile, invisible environment that the human body has never evolved to handle. Here is a mainstream fact. Measurements from the Curiosity rover's RAD instrument, made during its cruise to Mars in 2011 and 2012, showed that a human-equivalent astronaut on the same trip would receive a radiation dose of about 200 to 300 millisieverts, round trip. A one-way trip to Mars gives you roughly half of that. For comparison, that is around 100 to 150 times your natural background dose on Earth. Not all at once, but over the course of the voyage. If you add surface time on Mars, where the atmosphere is thin and there is no global magnetic field, you add several hundred more millisieverts. Total mission dose might approach 1,000 millisieverts or 1 sievert over a typical 2 to 3 year mission. That is a lot. Historians still argue over the precise health risks of this radiation dose. The standard epidemiological data is based on atomic bomb survivors, nuclear workers, and medical radiation patients, and extrapolating to deep space radiation is uncertain. But the mainstream estimate is that a sievert of deep space exposure raises a person's lifetime cancer risk by several percent, maybe 5 to 10%, which, depending on your optimism level, is either modest or appalling. It is not a death sentence, but it is also not nothing. The first Mars astronauts are buying themselves a non-trivial increase in their lifetime odds of serious illness. Light joke for tonight. Going to Mars is, in radiation terms, a little like choosing to live for 3 years inside a chest X-ray machine, except the machine also occasionally spikes the dose dramatically with no warning because a random sunspot decided it was time to have feelings. The radiation protocol for Mars missions basically consists of crouch low, hope for the best, and maybe hide behind the water tank during a solar storm, because water absorbs radiation pretty well. The quirky fringe tidbit is that some of the most dangerous radiation in interplanetary space comes from a specific class of particles called HZE particles, high atomic number, high energy ions. These are essentially nuclei of heavy atoms, stripped of their electrons, moving near the speed of light. When a single HZE particle slams into a human cell, it can tear through the cell like a bullet, damaging DNA, disrupting membranes, and leaving a trail of broken biochemistry. Most radiation hitting Earthbound cells is much gentler. HZE particles are a feature of deep space specifically, and biologists still do not fully understand how many HZD hits the human brain, nervous system, and gut can tolerate over months of exposure. Some animal studies have suggested that HZD exposure produces subtle cognitive effects, slight slowdowns in reaction time, slight memory issues that might matter over long missions. Physical shielding against radiation is, as you might expect, hard. Shielding mass is mass you have to launch, and rockets hate mass. The most effective shielding materials are, perhaps surprisingly, water and polyethylene plastic, because they contain lots of hydrogen, which scatters and absorbs energetic particles effectively. Metal shielding, like aluminum, is less effective and can even produce secondary radiation when high-energy particles slam into heavy atoms. So the best Mars mission shielding often takes the form of water tanks or plastic panels cleverly arranged around the crew's sleeping quarters. During a solar particle event, the crew retreats into the most shielded part of the ship, often a small storm shelter alcove lined with extra water and plastic, and waits for the storm to pass. The storm might last hours or days. The shelter is essentially a closet. Another mainstream fact: NASA's current career radiation limit for astronauts was recently updated to a harmonized limit of 600 millisieverts for most astronauts, regardless of sex or age, to reduce excess cancer risk to below 3%. A single long-duration Mars mission can approach or exceed this limit. This is one of the reasons why many Mars mission planners assume that Mars astronauts will essentially spend their full career radiation budget on a single mission, which, combined with all the other factors we'll discuss, adds yet another nudge toward stay on Mars. Second light joke tonight. Mars astronauts are, in radiation terms, essentially signing a lease for a 3-year stay inside a cosmic microwave oven with variable heating and no off switch. The brochure doesn't mention it, but it's there, in fine print, printed in a colour that is, by coincidence, the same as Martian dust. The fringe tidbit that few people know is that some researchers have proposed that Mars habitats be buried under several meters of Martian regolith, the dusty surface material, to provide passive radiation shielding once the astronauts land. Underground or regolith-covered habitats would dramatically reduce surface radiation exposure. But of course, building underground on Mars is its own engineering nightmare, involving digging, reinforcement, life support modification, and heavy equipment. The first missions will probably not have the capability to do any meaningful digging. They will live in lightly shielded surface habitats, accumulating dose year after year. Over time, this slow cumulative radiation exposure will further reduce the astronauts' fitness for the demanding stresses of a return journey, further nudging them towards staying. So the radiation picture by itself does not quite make the astronauts unable to return, but it nudges. It is fatiguing. It raises risks. It turns the question of return from a definitely into a maybe, depending on a lot of things. And when you start stacking these nudges, distance, launch windows, rocket equation, ISRU fragility, radiation, the answer starts tilting firmly in one direction. Remember the HZE particles, because they will come back in later sections when we talk about cognitive effects on the crew. Now gently, we turn to one of the most painfully quiet things that happens to a human body in space: bones. Your bones, if you cannot feel them right now, are doing an extraordinary job of holding you up. They are living tissue, not the dry white shapes you have seen in anatomy books. Your bones are constantly being broken down and rebuilt, every day, in a quiet biological remodel that is so continuous you never notice it. On Earth, the process is balanced. New bone is added at roughly the rate that old bone is removed, because gravity constantly pulls on your skeleton, and the cells inside your bones use that tug to calibrate where to strengthen and where to spare effort. Gravity is, in a real sense, your bone's drill sergeant. Now imagine taking that drill sergeant away. Imagine floating. No gravity, or only the tiny microgravity of freefall. The cells in your bones notice. They do not understand immediately that you are in space. They only know that the usual forces are gone, and their response on average is to slow down the rebuilding process while the removal process continues. The result, month after month, is bone loss. Here is the mainstream fact to file in your pillow. Astronauts on the International Space Station typically lose bone mass at a rate of about 1 to 1.5% per month. Per month. Cumulatively, over a 6-month mission, that is several percent of their total bone mass, mostly from the weight-bearing areas like the hips, spine and legs. Over the full 9-month transit to Mars, astronauts could lose somewhere between 10 and 15% of the bone mineral density in their critical weight-bearing bones. 10 to 15%, comparable to what older adults lose over years of osteoporosis. Historians still argue over how much of this bone loss is recoverable after a return to gravity. Studies of astronauts returning from long ISS missions suggest that most recover within 1 to several years, but not all of the bone loss is reversed. Some density is apparently permanent. Worse, the bones that do recover may recover incompletely, with new bone that is slightly less structurally organised. Fracture risk may remain elevated, and the longer the time in microgravity, the harder the recovery. Light joke for tonight, space is essentially a very expensive way to give yourself a decade's worth of age in a year. The bones do it, the muscles do it, the eyes do it, the cardiovascular system does it. Going to Mars and spending 2 years there is a bit like fast-forwarding through a portion of your natural aging process in exchange for some really interesting photos of sand dunes, which, honestly, fair trade for some people. The quirky fringe tidbit is that your bones are not the only thing losing density. Your teeth may also change subtly, because dental bone is part of the same remodeling system. Astronauts returning from long missions sometimes report minor dental issues, though the research is still developing. Your spine, meanwhile, elongates slightly in microgravity, because the intervertebral discs expand without the usual compression. Astronauts can gain several centimeters of height in space. The effect reverses when they return to Earth, but the brief space stretch is real, and it produces back pain as the discs readjust to gravity. Now let's specifically examine what this means for the Mars journey. Over the 9-month transit, the astronauts lose substantial bone mass. They arrive on Mars with weakened skeletons. Mars gravity is about 38% of Earth's gravity, which is not zero, but it is not enough on current evidence to fully halt bone loss. It is a partial reprieve, not a cure. During the 500-plus days they spend on Mars, they may continue to lose bone, though more slowly than in zero-G. By the time they climb into the MAV for the return journey, their skeletons are significantly less dense than they were when they left Earth. Then, if they somehow return, they face the stress of re-entry, gravity readjustment and rehabilitation, all with weaker bones than they started with. A second light joke. An astronaut returning to Earth after a Mars mission is essentially a human body being handed a physics exam they have not studied for in 3 years. Here is gravity. You remember gravity, right? It is still 1G here. Please stand up. Yes, that's right. Now please do not fall over. Oh, that's unfortunate. Okay, we'll help you up. The rehabilitation programs for returning astronauts are not small. They involve months of careful physical therapy, bone density monitoring, and gradual reintroduction to terrestrial activity, and that is for astronauts who only went to the ISS Mars astronauts after a 2 to 3 year mission would face a much harder recovery. Here is another mainstream fact. NASA and other space agencies have developed protocols to slow bone loss in space. Astronauts on the ISS exercise for about 2 hours per day using specialized equipment, the Advanced Resistive Exercise Device, or ARED, the treadmill and the bike. The exercise is intense and well designed. It reduces bone loss significantly, but does not eliminate it. Medications like bisphosphonates have also been tested on ISS crews and appear to help. But none of these countermeasures are perfect. A Mars mission crew would be using similar countermeasures throughout their journey and stay, but the cumulative loss would still likely be greater than anything an ISS crew faces. The fringe tidbit to carry into the night is that some researchers have proposed that the solution to bone loss on long missions is artificial gravity. If the spacecraft slowly rotates, for instance, as a giant wheel or with a tether configuration, the resulting centrifugal force would mimic gravity and keep the astronauts' bones loaded. This idea has been around since at least Wernher von Braun's designs in the 1950s and 1960s. Artificial gravity would, in principle, solve many of the biomedical problems of deep space travel. But building a rotating spacecraft is harder than it sounds. The rotating components add mass, complexity, and failure modes. No large rotating spacecraft has ever flown. Some future Mars missions may adopt variable gravity architectures. The first missions will almost certainly use zero-G capsules and will accept the bone loss cost. Historians still argue whether a truly safe, long-duration Mars mission is possible without artificial gravity. Some physicians are optimistic about countermeasures. Others are skeptical. The answer is, frankly, not yet known. The first humans to go to Mars will essentially be the human research subjects for this question. They will return, if they return, with measurements of how their bodies actually handled 2 or 3 years of reduced gravity. Those measurements will be priceless scientifically and deeply expensive personally. Sit with this for a moment. Every astronaut who has spent long months in microgravity has come back with somewhat thinner bones. Everyone. The effect is consistent, it is well documented, and it is, in its quiet way, part of the reason why the first humans on Mars will have a hard time coming back. Not because the rockets can't fly, but because the people inside the rockets are gradually being remade by the trip. And a remade person is, in a very literal sense, not quite the same person who left Earth. That is not a tragedy. That is just physics, meeting biology, at a speed measured in millimeters per year. Remember the gradually thinning spine and the stretching height, because in the next section we'll zoom in on how Mars gravity specifically rewrites the rest of your body. Your bones are not the only thing the trip is remaking. Your entire body, head to toe, is quietly recalibrating itself for a reduced gravity environment. Muscles, heart, eyes, blood, immune system. All of them are taking advantage of the vacation from gravity to stop working as hard. By the time you reach Mars, you are not the person you were when you left Earth. You are a leaner, stretchier, slightly weirder version of that person. And during your months on Mars under a gravity that is only about 38% of Earth's, your body continues to adjust further, in ways that are, quite honestly, irreversible without extreme effort. Start with the muscles. Muscles, like bones, are maintained by use. On Earth, just walking around does a huge amount of work for your leg muscles. Your calves, thighs, glutes, core and back are all constantly firing in small adjustments to keep you upright and balanced. You do not notice this work because it is automatic. Remove gravity, and those muscles get suddenly idle. They notice, they adjust, they shrink. Here is the mainstream fact. Astronauts on the ISS lose muscle mass at a rate of about 1 to 2% per week if they do not exercise vigorously. per week. A 6-month ISS mission without exercise would essentially cripple an astronaut by the time they returned. This is why ISS crews exercise so fanatically, for 2 hours a day, every day. Even with that much exercise, some muscle loss still occurs, especially in the postural muscles that are not easy to target with standard gym equipment. Now extrapolate to Mars. 9 months in transit at 0G, 500 plus days on Mars at 38% gravity, 9 more months of transit back at 0G. By the time the astronauts are climbing into the Mavi for the return leg, their muscles have been working at reduced loads for well over a year. Even with diligent exercise, they're weaker than when they left. And muscle, unlike some tissues, is relatively fast to recover with training. But the training has to happen somewhere. And if you are still on Mars, you're still in reduced gravity, which makes full recovery basically impossible. Historians still argue over the optimal exercise regimen for long-duration Mars missions. Some physiologists favour intense resistance training, high loads, fewer reps. Others favour longer endurance sessions with lighter loads. Most agree that a combination is necessary, but all of them concede that the best exercise on Mars is not as good as simply existing on Earth. Your body, on Earth, is always being loaded by gravity. You're always doing low-grade strength training, every second of every day. On Mars, you get about a third of that daily workout, whether you want it or not. The difference accumulates. Light joke for tonight. Mars astronauts will essentially be members of the world's most exclusive gym, where membership is non-refundable, the equipment is maintained by engineers who are also doing the workouts, and the penalty for skipping a session is, quite literally, falling apart slightly. The motivation to exercise is high. The rewards are modest. The downside of not exercising is visible in the mirror, slowly over months. Now let's talk about the eyes. This is a strange and less known effect. Astronauts on long missions sometimes develop a condition called spaceflight-associated neuroocular syndrome, or SANS. It affects vision. It seems to be related to fluid shifts in the body. Without gravity, body fluids redistribute toward the head and upper body, and the pressure on the optic nerve changes. Over months, this can cause actual physical changes in the eye. Some astronauts have returned from long ISS missions with noticeably altered eyesight, and not all of them have fully recovered. Nobody's going blind. But some are wearing stronger glasses. Some have small, permanent changes in the structure of their retinas and optic discs. For a Mars mission 2 to 3 years long, the risk is magnified. Historians still argue whether SANS is fully reversible, or whether some percentage of affected astronauts keep altered vision permanently. Studies of ISS crews are ongoing, with better imaging each year. The medical community is on the case. But the bottom line is that space, for reasons involving fluid dynamics and pressure distribution inside the skull, is not friendly to human eyes. Mars astronauts will probably come back needing new glasses at the least, and possibly with more serious changes. Here is the quirky, fringe tidbit. Some researchers have proposed that the fluid shifts that cause SANS also affect the brain. Brain imaging of astronauts before and after long missions has shown small changes in cerebrospinal fluid volumes, in ventricle sizes, and in the positioning of certain structures. These changes are mostly small, and their implications are uncertain, but they are real. The human brain in 0G for 6 months is not exactly the same brain afterward. For a Mars crew out for 2 to 3 years, the cumulative effects are basically a science experiment in real time. Now zoom down further. The immune system also changes in space. Astronauts often experience a dampened immune response during missions, with some viruses, like herpes zoster and Epstein-Barr, becoming reactivated. The thymus gland, where some immune cells mature, appears to atrophy slightly. The gut microbiome shifts too because nutrition is different, and low gravity changes how food moves through your intestines. The result is that astronauts come back slightly more susceptible to infection, slightly more vulnerable to latent viruses, and with rearranged internal ecosystems that can take months to stabilize. Like joke time, going to Mars is essentially an extremely expensive way to simulate the symptoms of aging. Bones thinning? Check. Muscles wasting? Check. Eyes changing? Check. Cardiovascular system remodeling? Check. Immune system getting picky? Check. By the time you return, if you return, you have essentially fast-forwarded part of the aging process, and you have the medical records to prove it. On the upside, you have also arguably been to Mars. On the downside, you have medically been to the emergency room. Here is another mainstream fact about Mars gravity specifically. We do not actually know, with certainty, how human bodies respond to 38% gravity over months or years. Nobody has ever lived in Mars gravity. All our data is from 0G or from brief stints at simulated lunar gravity. Mars gravity is intermediate, and we are honestly guessing about its effects. Some researchers argue that Mars gravity will be enough to preserve most bone and muscle mass with appropriate exercise. Others argue that it will only slightly slow the losses seen in 0G. The first humans on Mars will provide the data. They are, in a sense, Earth's first volunteer subjects in an experiment nobody has ever run before. The fringe tidbit to sleep on is that some biologists have hypothesized that human pregnancy and fetal development in Mars gravity might not work the way it does on Earth. Fetal bones, fetal muscles, fetal cardiovascular systems might all develop differently. Nobody has ever tested this. No mammal has ever gestated in lunar or Martian gravity. If Mars colonies grow, the first Mars-born humans will be the first data point in a developmental biology question that nobody has answered. We will talk more about Mars-born children in a later section. Remember the stretching spine, the thinning bones, the weaker muscles, the remodeling heart. Yes, heart, that's next. Because every one of these changes reduces the astronaut's fitness for the demanding task of return. Slowly, very slowly, biology is voting. Now we turn to one of the most elegant and unsettling discoveries about the human body in space, the heart. Your heart, that faithful little fist-sized pump that has been keeping you alive every second of your life, is, it turns out, quietly reshaping itself in low gravity. Not catastrophically, not even uncomfortably, but measurably. And the direction of the change is, of all things, round. Here is the mainstream fact. A study published in 2014 by researchers at Michigan State University and others, using ultrasound imaging of astronauts before, during and after long missions on the ISS, found that the human heart becomes more spherical in microgravity. On Earth, your heart has a particular elongated, ovalish shape, stretched along its long axis. In space, without gravity to pull on it, the heart relaxes into a slightly more rounded form. The effect was measurable. The hearts became about 9.5% more spherical on average during 6-month missions. After return to Earth, the hearts mostly resumed their Earth shapes, but the transient remodeling was real and consistent. You can almost feel the strangeness of this. Your heart, an organ you have never thought about in terms of geometry, is apparently a shapeshifter. Gravity, it turns out, is not just pulling on your feet. It is pulling on every organ in your chest. Your heart, your lungs, your liver, your kidneys. All of them are slightly compressed and shaped by the gentle tug of Earth's gravity. Remove that tug, and they redistribute. Historians still argue whether the heart's sphericization has real long-term health consequences. During the mission, cardiac function seems fine. After returning, the changes seem to reverse. But some researchers worry that over much longer durations, say the 2 to 3 years of a Mars mission, the cardiac remodeling might be more pronounced and recovery might be less complete. We simply do not have the data for multi-year missions. Nobody has been in space that long. The quirky, fringe tidbit for tonight is that the heart is not the only organ that shapeshifts in space. The entire cardiovascular system adapts, blood volume decreases. The body seems to sense that it does not need as much fluid to move against gravity, and it sheds some. Astronauts returning to Earth often experience orthostatic intolerance. They cannot stand up without feeling faint, because their cardiovascular system has lost the reflexes to quickly pump blood against gravity to their brains. It takes weeks to months to fully recover. For Mars astronauts, who would face this issue after 2 or 3 years in reduced gravity, the recovery would be significantly harder. Light joke for tonight. Your heart is essentially a loyal employee who, given a long break, slowly relaxes into a softer, rounder form, puts on a cardigan, and by the time you want it back at work, it politely asks if maybe it could work remotely forever. The recovery of cardiac fitness after a long mission is possible, but requires genuine effort. Let's get specific about what a weakened cardiovascular system means on the return trip. The astronauts leave Mars in the MAV. They endure the G-forces of ascent, which on Mars are relatively modest because Mars's gravity is low. They rendezvous with the Earth return vehicle in Mars orbit. They begin the cruise back. This is another 9 months or so of zero G, during which their bodies continue to decondition. When they finally arrive at Earth, they face re-entry, which involves substantial G-forces, typically several G, as the spacecraft decelerates through Earth's atmosphere. Re-entering Earth's atmosphere is physically demanding even for astronauts in peak condition. For astronauts who have been away from Earth gravity for 2 to 3 years, whose hearts are differently shaped, whose blood volumes are reduced, whose muscles are weakened, the re-entry itself becomes a dangerous medical event. Some astronauts might not survive it. Others might survive it but arrive on Earth in severely compromised condition. Historians still argue whether the best return profile involves minimizing G-forces, perhaps with a long, slow aero-braking sequence, or accepting higher G-forces with a faster return. The trade-offs are between radiation dose, longer in space, more radiation, and cardiovascular stress, shorter with higher G-forces. Neither is comfortable. Another mainstream fact. NASA's twin study, published in 2019, is one of the most detailed looks we have at long-duration spaceflight effects on the human body. It compared Scott Kelly, who spent nearly a year on the ISS, to his twin brother Mark, who stayed on Earth. The results showed numerous physiological and even epigenetic changes in Scott, some of which persisted after his return. Some gene expression patterns did not fully return to baseline. His carotid artery showed some thickening. His telomeres, the protective caps on chromosomes often associated with aging, initially lengthened in space and then shortened back with disruption on return. The body, in short, is deeply rearranged by long spaceflight in ways we're only beginning to understand. The second light joke tonight. Mars astronauts will essentially spend 3 years as the most expensive medical research subjects in human history, generating a dataset that physiologists will study for a century. The subjects will be told, politely, that their sacrifices will help future astronauts prepare better. The subjects will nod, understanding. Then they will try to stand up on Earth if they make it back, and they will feel, in a very immediate and personal way, exactly how much data they have just generated. The fringe tidbit to carry into sleep is that some researchers have proposed that long-duration astronauts might eventually become so adapted to low gravity that returning to Earth becomes dangerous rather than merely uncomfortable. In principle, after enough time in Mars gravity, the cardiovascular system might lose the capacity to function at Earth's gravity altogether, without months or years of rehabilitation. If astronauts stay on Mars long enough, the window for safe return might close. This is one of the strangest arguments in Mars mission planning. Some engineers have suggested that beyond a certain duration, maybe 2 years, maybe 3, maybe more, returning to Earth becomes medically inadvisable. Regardless of the rocket engineering, the mission becomes, in effect, permanent. This is a strange thought to hold in your sleepy mind. You go to Mars, you stay a little too long, and then, one day, you realize that even if the rockets could take you home, your body cannot. The choice has been made without being made. Your cardiovascular system casts the deciding vote. Historians still argue whether this scenario is realistic or exaggerated. The human body is resilient. Recovery is possible from many kinds of spaceflight deconditioning. But there is a tipping point somewhere, beyond which rehabilitation becomes too hard, too long, too uncertain. The first Mars astronauts may or may not cross it. The ones who stay the longest, probably yes. Remember the sphericized heart, the reduced blood volume, the orthostatic intolerance. These are not dramatic injuries. They are quiet, accumulating changes. They are what happens when you spend several years somewhere else. Next, we zoom in on a population that will not even have an Earth version of their body to begin with. The first children born on Mars. Imagine tonight a child, a small one, maybe 5 years old, with reddish dust in the corners of their shoes, with a quiet laugh, with eyes that have never seen an Earth sky. Born on Mars, maybe in a sealed habitat, maybe in a pressurized dome with slowly reinforced regolith walls, named by parents who once walked on Earth, but who will probably never walk there again. This child, this little Martian human, is quite possibly one of the most biologically unique beings who has ever existed. And this child cannot go to Earth. Not safely. Not without consequences. Probably not at all. Let's think carefully about why. This child's bones grew in Mars gravity. Mars gravity is about 38% of Earth's, so this child's bones have been calibrated from fetal development onward for a much lighter load. Their skeletal density, their skeletal geometry, their bone muscle attachments, all of it has been adapted to a world where a grown adult weighs around 60% less than they would on Earth. If this child was suddenly placed on Earth, their bones would, quite literally, be trying to hold up a body 2.5 times heavier than the body they grew up with. Their legs might not support them standing. Their spine might buckle. Their ribs might compress. Simple walking might be impossible. Historians still argue over exactly how severe these effects would be, because nobody has ever raised a mammal in Mars gravity. All the studies are on Earth animals briefly exposed to microgravity or hypergravity, but the general consensus among developmental biologists is that gravity strongly influences bone and muscle development during growth. A person who has never experienced Earth gravity during their developmental years would be physically ill-equipped for it afterward. Here is the mainstream fact. Bone and muscle development in childhood is gravity dependent. Studies of children who grow up on Earth but are bedridden for long periods, or who suffer from certain neuromuscular conditions, show that their bones develop differently. They become smaller, thinner, and more fragile. The effect is partly reversible with rehabilitation, but not fully. A Mars-born child who has experienced Mars gravity from conception onward would be, in a sense, a different kind of human physiologically. Not dramatically different to look at, but significantly different under stress. Light joke tonight. Mars-born children will essentially be the first Martians, in the honest, literal, science fiction sense. Not just humans who move to Mars, but humans who are made by Mars. Their feet will be shaped by Mars gravity. Their lungs will be shaped by Mars habitat atmospheres. Their gut microbiomes will be shaped by recycled water and a limited diet. Even their cultural habits will be shaped by Martian routines. They are, in every meaningful sense, native to a planet that Earth has been studying with telescopes for centuries, and some of them may look at Earth on a screen and not feel particularly connected to it. Here is the quirky, fringe tidbit. No mammal has ever been conceived, gestated, born, and raised to reproductive adulthood in a gravity significantly different from Earth's. The closest experiments have involved rats briefly flown on the space shuttle, including pregnant rats whose offspring were born on the ground but had microgravity exposure during gestation. Those offspring showed some subtle developmental differences but were broadly healthy. Longer experiments in zero-G have not yet produced a full mammalian life cycle. We do not know if mammals can even reproduce normally in zero-G or in Mars gravity. We suspect yes, we are not certain. The first Mars colony, if it produces children, will answer this question definitively, and the answer may have surprises. Historians still argue over whether human reproduction on Mars should even be attempted in the first few generations, precisely because the developmental biology is so unknown. Some bioethicists have proposed that first-generation Mars colonists should avoid having children until there is more data. Others argue that preventing reproduction is itself a violation of colonists' rights, and that the biology should be allowed to unfold carefully with medical support. The debate is vigorous, and it has not yet settled. Science fiction has explored it endlessly. Real-world policy has barely begun. Let's sit with the image of that Mars-born child for another sleepy moment. They have never felt rain. They have never felt wind strong enough to pick up a leaf. They have never stood in direct sunlight without a helmet. They have never seen a blue sky of the earthly kind. They have never heard of birds. They have never petted a dog. Their world is pressurized, recycled, engineered and small, and yet to them, it is home. It is everything. Earth is a legend, a place their parents sometimes talk about with a tone of voice that shifts slightly between nostalgia and silence. Earth is, to this child, a bit like Atlantis is to us. A beautiful myth, possibly real, possibly not worth the trip. A second light joke. The first Mars-born human will eventually be asked by a reporter, via a 20-minute round-trip interview, "What do you want to be when you grow up?" And the child will look politely at the camera and say, "I'd like to fix air filters for a living. The air filters are very important. My parents depend on them." And the reporter, 40 minutes later, will ask a follow-up about astronaut dreams, and the child will patiently explain all over again that air filters are genuinely cool. Here is another mainstream fact. For long-term Mars colonization to succeed beyond the first generation, colonists must reproduce on Mars. Otherwise, the colony is a kind of cultural and biological Ponzi scheme, requiring constant shipments of Earth people to sustain itself. True colonization means children. Children mean Mars-native humans. Mars-native humans mean biology that has never been tested, and that biology, once established, makes return to Earth effectively impossible for those who were born there. The colony, once it produces a generation of native Martians, has irreversibly forked from the terrestrial human gene life story. Some of those children may still, with careful medical preparation, visit Earth briefly as adults. Others may never be able to. The fringe tidbit to tuck into the night is that some researchers have speculated about what a few generations of human life on Mars would do to our species on longer timescales. If Mars colonists reproduce for centuries, selection pressures unique to Mars might begin acting on their gene pool. Low gravity, low pressure, high radiation, controlled nutrition, small population effects. Over centuries, these pressures could slowly push Mars humans in directions slightly divergent from Earth humans. Not a different species, certainly not in any short time scale, but perhaps slightly different, slightly taller on average, slightly lighter boned, slightly more radiation tolerant, slightly more adapted. These speculations are fun to imagine but deeply uncertain. What is clearer is the immediate developmental issue. A child born on Mars today is already in practical terms not built for Earth. Remember this child because they embody, in miniature, the entire argument of tonight's script. The first humans on Mars will not come back. Their children will not come back. Their grandchildren, in all likelihood, will also not come back. Mars is not a destination. Mars is a destination that becomes a departure point for a new branch of human existence. Next, we look at what the journey there does to the human mind. Let's pause the biology for a breath and think about the mind. Because going to Mars is not just a physiological ordeal, it is also an extraordinary psychological one. 9 months in a tin can with 5 other humans, drifting across a dark, silent, enormous vacuum, then 500 days in a cramped habitat on a hostile planet, then 9 more months back maybe, or not. The psychological weight of such a journey is hard to fully imagine from Earth, but psychologists have been trying for decades to model it. Here is the setting. Your spacecraft is at best about the size of a small house. The crew is small, maybe 4, maybe 6. You share every meal, every conversation, every sleep schedule, every bathroom break. You know every colleague's sneeze pattern, every snoring cadence, every joke they tell when they're tired, every quirk of how they chew. You know, within a week or 2, everything any human can know about 5 other people at close range. After that, you know it deeper, and deeper, for months. Here is the mainstream fact. Antarctic winter-over crews who spend 6 to 9 months at isolated research stations have been the terrestrial analogue most studied for Mars-like psychology. These crews are carefully selected for psychological resilience. They are well trained, they have adequate supplies, they have radio and internet contact with the outside world, and they still experience significant psychological stress. Depression, insomnia, cognitive fatigue, interpersonal friction, and occasional minor breakdowns are common, even in the best selected crews. The winter-over phenomenon, a depressive, sluggish mood state that sets in during the long polar winter, is well documented. Now project that onto a Mars mission. The crew is more isolated, communication delay is significant, physical space is smaller, there is no option to abort and fly out, the stress is longer, the consequences of interpersonal conflict are much higher, because the crew depends on each other for survival every day. Historians still argue over whether Mars crews will crack psychologically during long missions, or whether careful selection and training will be enough to prevent serious problems. There are no real-world data yet. The closest experiments are ground simulations, long habitat stays in isolation, which produce some useful data but do not capture all the stresses of real interplanetary travel. Light joke for tonight. Mars astronauts are essentially signing up for the world's most intense roommate arrangement. Imagine a college dorm but smaller. Imagine that the roommates are also your co-workers, your emergency medical team, your dinner conversation partners, and your entire social universe for 3 years. Imagine that there are no weekends, no vacations, no parents visiting. You love your roommates. You learn to love them, because the alternative is horrifying. And by the end, you know them so well that when you come back to Earth, regular social interaction feels strangely thin and shallow by comparison. The quirky fringe tidbit is the story of Mars 500, an experiment conducted by the Russian Space Agency and the European Space Agency from 2010 to 2011. 6 male volunteers spent 520 days in an isolated facility in Moscow, simulating a full Mars mission round trip, including a simulated Mars landing. They had no real external communication, only simulated one-way delays. They ate the same food, maintained the same exercise routines, and performed the same types of experiments that would be expected of real Mars astronauts. The experiment provided a treasure trove of data about interpersonal dynamics, cognitive performance, sleep cycles, and mood in long-duration isolation. Most of the crew remained functional, but there were periods of fatigue, mood disturbances, altered sleep patterns, and interpersonal tension. And this was just a simulation. The stresses of actual Mars travel, real danger, real isolation, real bodies being remade by microgravity, would be greater. Here is another mainstream fact. Sleep is particularly vulnerable during long missions. Astronauts on the ISS average only about 6 hours of sleep per night, significantly less than the recommended 7 to 9. The causes include noise, light, habitat design, excitement, stress, and the absence of normal day-night cycles. Chronic sleep deprivation has serious cognitive and emotional consequences. Mars astronauts would face these issues for 2 to 3 years continuously. Strategies to mitigate sleep loss, including carefully engineered lighting, soundproofed sleeping quarters, melatonin protocols, and scheduled rest periods, are part of modern mission planning. But they cannot fully solve the problem. Long-term sleep debt is a real risk on a Mars mission. A second light joke tonight. Sleep on a Mars mission is essentially a limited resource, like water, like oxygen, like patience with your crewmates. Everybody rations it. Everybody resents the rationing. Everybody knows that without it, things will slowly break down. On the rare occasion when an astronaut gets 8 unbroken hours, they treat it like a cosmic gift. They wake up slightly less sarcastic. The rest of the crew notices. Everybody is a little kinder that day. Here is another piece of quiet psychology. Homesickness. The astronauts are not just isolated from other humans, they're isolated from Earth itself. They see it as a blue marble through a small window slowly shrinking as they depart. They cannot smell Earth air, they cannot feel Earth rain, they cannot hold Earth people. They are, in a very specific and unprecedented sense, separated from the biosphere that made them. This separation produces a psychological effect that does not have a clean name but is sometimes called Earth-gazing. Astronauts returning from long missions often describe a deepened sense of Earth as home, a kind of tender, possessive love. For Mars crews who would be separated from Earth for years and who might never return, this Earth-gazing becomes something else, a kind of anticipatory grief, a quiet mourning for a world that still exists but is now, in practical terms, out of reach. The fringe tidbit for tonight is that some psychologists have suggested that the first Mars crews should include specialists specifically trained in counselling and small group dynamics, not just astronauts who happen to be good at teamwork. The idea of a dedicated crew psychologist, a trained therapist whose main mission is to keep the crew functional, has been proposed in various forms. It is controversial. Some argue that all crew members should be trained in some counselling techniques, so that nobody is the designated therapy person. Others argue that specialisation is efficient and necessary. The first missions may experiment with different models. Historians still argue over the ideal composition of a Mars crew. Should they be all technical specialists, maximising engineering competence? Should they include humanities-trained members to help with meaning-making during the journey? Should they include married couples to provide natural support pairs? Should they be all same-sex, all different sex, or mixed? Each configuration has trade-offs. There is no clean answer. The first missions will almost certainly be small, tightly selected and carefully trained. The first few crews will probably be looked back on as pioneers whose exact composition shaped everything that followed. Sit with this for a moment. 6 people in a small tin can for years. The last human voice you hear in real time before departure is a controller in Houston saying Godspeed. The first human voice you hear in real time after arrival, if ever, is not quite in real time because of the communication delay. For years, your entire universe is 5 other humans and 1 small ship, and then 1 small habitat, and the nighttime sky of a planet most of Earth has never touched. Remember this, because the next section looks at the specific torture of communication delay. You pick up the phone, or rather the radio. You want to say something to someone back on Earth, maybe your mother, maybe a friend, maybe your spouse. You speak into the microphone. You record the message, you transmit it, and then you wait. Because your message is now a beam of radio energy, travelling through space at the speed of light, and even at the speed of light, getting to Earth takes time, and getting a reply takes time, and sometimes the amount of time involved is long enough to break any ordinary conversation. Here is the basic physics. Radio waves travel at the speed of light, roughly 300,000 kilometers per second. When Mars and Earth are at their closest, a radio message takes about 3 minutes one way, 3 minutes to reach Earth, 3 minutes for the reply to come back. 6-minute round trip minimum. When Mars and Earth are farthest apart, the one-way delay is over 20 minutes, over 40-minute round trip. So if you send a quick, "Hi, how are you ancestral to Earth?" you have to wait up to 44 minutes for your loved one to even hear it and respond. If you say "I miss you," you have to wait for up to 44 minutes for any acknowledgement. There is no real-time conversation possible with Earth from Mars. None. Ever. The physics simply does not allow it. Here is the mainstream fact. This is exactly how Earth currently communicates with Mars rovers and orbiters. NASA's Perseverance, for example, operates with a significant command delay. Engineers send a day's worth of commands at once, and the rover executes them and then sends back telemetry, which engineers examine the next day. There is no joystick control from Earth. The rover is essentially semi-autonomous because of the delay. For crewed missions, the same delay applies to human conversation. Text messages, voice messages, video messages, all of them are delayed. Nobody on Mars will ever have an immediate phone call with someone on Earth. They will only have slow correspondence. It will feel at times like the age of sailing ships and long letters. Historians still argue over how the communication delay will affect the psychology of Mars crews. Some psychologists worry that it will deepen the sense of isolation. Others argue that it may actually reduce the meddling of Earth-based mission control, giving the crew more autonomy and agency. Both may be true. The crew will feel more alone. The crew will also feel more in charge. It is a strange trade. Light joke for tonight. Mars astronauts will essentially re-experience the pace of 19th century transatlantic correspondence, except the letters are digital and the ocean is 200 million kilometers of vacuum. You write, you send, you wait, you receive, you read, you write again. It is in some ways a more deliberate form of communication than modern text messaging. You cannot fire off a quick reply. Every message takes thought, because every message is going to sit in transit for up to 20 minutes before anyone reads it. You become a better writer, out of necessity. Here is the quirky fringe tidbit. Because of the communication delay, Mars astronauts will essentially need to be trained in asynchronous life. This is, technically, a skill. People who work in distributed teams across time zones already practice it. You cannot ask quick questions. You cannot brainstorm in real time. You have to write detailed, context-rich messages because the recipient will not have the ability to ask clarifying questions without another 20-minute delay. You have to anticipate the other person's questions in advance and answer them preemptively. Over months, this becomes a natural rhythm. The crew and Earth develop a kind of slow, careful, epistolary relationship. It is, in its own way, beautiful, but it is also deeply different from any form of communication most humans have ever lived with full-time. A second light joke. Imagine trying to argue with a family member while there is a 40-minute delay between each message. By the time they respond to your angry message, you have already calmed down, had coffee, reconsidered, sent a follow-up, apologised, and made a reasonable compromise. Their response arrives just as you're taking a nap. Arguments on Mars are, in this sense, automatically de-escalated by the speed of light. It is the universe's gentlest conflict resolution mechanism. Here is another mainstream fact. Internet access, in the form Earthlings know it, is essentially impossible on Mars. Streaming video, real-time social media, live video calls, all of them require low latency. The minimum latency to Mars is about 3 minutes, one way. The maximum is over 20. So Mars astronauts will not be doom-scrolling social media. They will not be watching live sports. They will not be playing online video games against people on Earth. They will have access to cached content, movies, books, music, downloaded websites. But fresh content will arrive in batches, maybe daily or weekly, as bulk downloads. The experience is less like internet, and more like mail service. Historians still argue over how this will affect Mars crew's sense of connection to global events. Some worry that astronauts will feel increasingly disconnected from the Earth news cycle. Others argue that they will become more thoughtful, reading in depth rather than skimming. Now think about family. Imagine you have a partner on Earth. You met before the mission. You agreed that 3 years apart was survivable because you would return. And then you realise that you will not return. What does your relationship look like? Across 40 minutes of delay, across months and then years of separation, with the growing knowledge that you will never physically be in the same room again. Can the relationship survive? For some, yes, probably. For others, no. Many Mars astronauts will return from their mission, or rather will not return, to find their personal lives on Earth have shifted fundamentally. Partners move on. Parents age. Friends drift. The Earth you left is not the Earth you correspond with, and even that Earth is not the Earth you would have if you could go back. The fringe tidbit for tonight is that some philosophers and communication theorists have wondered whether, over long durations, the Mars crew's inner Earth will start to diverge from the actual Earth. Their mental model of Earth, based on delayed correspondence, cached news and memories, will freeze in certain ways, even as Earth itself keeps changing. By year 3, the Mars crew's imagined Earth may look slightly outdated, a little like the Earth of the year they left while Earth has moved on. This effect is sometimes called cultural lag. It is small at first. It grows. Long-term Mars colonists may eventually find that their Earth knowledge is essentially historical. Historians still argue over how much this cultural lag matters. Optimists argue that with good communication infrastructure, Mars crews can keep up with Earth trends almost in real time, just with delays. Pessimists argue that the emotional bonds weaken even if the information reaches. The truth is probably somewhere in the middle. Mars astronauts will know, intellectually, what is happening on Earth. They just won't feel it the same way. Earth will become, slowly, a story they follow, not a world they inhabit. Remember the 40-minute round trip, because every time you imagine a Mars astronaut calling home, remember that their mother, if she is lucky, will hear their voice about 20 minutes after they say the words, and the child will have to wait another 20 minutes to hear her reply. Next, we examine what happens when someone on Mars gets really genuinely sick. You are on Mars, 225 million kilometers from the nearest hospital. You wake up at 3 in the morning Mars time with a sharp pain in your lower right abdomen. It does not go away. It gets worse. By morning you suspect appendicitis. You have a crew medic. The medic has training. The medic has equipment. The medic is also one of the 5 other people in this habitat who depends on you to survive. This is what medical emergencies look like on Mars. Here is the basic problem. On Earth, a case of appendicitis is generally a manageable medical event. You go to the hospital, a surgeon evaluates you. An hour or 2 in the operating room and you are recovering. Antibiotics, pain management, a few days in bed. You're back on your feet in a week. It is unpleasant, but it is not a tragedy. You're statistically much more likely to survive appendicitis than to die from it. On Mars, appendicitis is a very different animal. The nearest surgeon is many months away by spacecraft. Communication with Earth has a one-way delay of up to 20 minutes. The surgical equipment you have is what fits in a medical kit sized for a crew of 6. Your crew medic is a highly trained generalist who has practiced appendectomies in simulators, but may never have performed one on a real human under real conditions. The surgical environment is a small medical bay with limited sterility, limited anesthesia options, and limited backup if something goes wrong. The historical record of medical emergencies in extreme remote settings is instructive and a little terrifying. There is a famous case from 1961 at a Soviet Antarctic research station, where a physician named Leonid Rogosov developed appendicitis during the winter when no evacuation was possible. He performed his own appendectomy on himself, with the assistance of 2 non-medical colleagues who held mirrors and handed him instruments. He survived. He became a legend. Historians still argue whether his improvised surgery represents heroism, cleverness, desperation, or some combination of all 3, but the core fact stands. He cut out his own appendix because there was no alternative, and he lived to tell about it. Here is the mainstream fact for Mars missions. Medical emergencies are one of the top-ranked risks in Mars mission planning. NASA and other agencies have developed extensive telemedicine protocols in which Earth-based specialists advise crew medics via delayed communication. Advanced medical kits, with semi-automated diagnostic tools and surgical assistance systems, have been in development for years. Some crews will include more than 1 person with medical training, in case the primary medic becomes the patient. Still, the reality is that certain serious medical events, strokes, heart attacks, severe trauma, cancer, sepsis, may be essentially untreatable in a Mars setting. Historians still argue over what kinds of medical care should be available to Mars crews. Some argue for advanced robotic surgery systems, capable of performing delicate operations under remote Earth guidance. Others argue that such systems are too complex and failure-prone, and that simple, reliable manual tools are better. The debate is ongoing. The reality is probably a mix. Whatever the Mars crews bring, they bring a fraction of what a modern hospital has. Light joke for tonight. Mars is, medically speaking, the worst place in the solar system to get a paper cut. Not because the paper cut will kill you, but because the paper cut will be disproportionately annoying, since you cannot just go to a pharmacy and your first aid kit is rationed. For anything more serious than a paper cut, the stakes escalate rapidly. Appendicitis, serious. Kidney stones, very serious. Heart attack, potentially fatal. Serious trauma, probably fatal. Cancer, essentially untreatable at any advanced stage. The medical safety net that Earth life takes for granted simply does not exist. The quirky fringe tidbit is that Mars missions may face medical problems that do not exist on Earth in any significant form. Long-duration radiation exposure may produce cancer rates somewhat elevated over baseline. Microgravity may produce unusual blood clotting events. There is already evidence from ISS crews of unusual jugular vein clots in some astronauts, which is a cardiovascular risk that essentially does not occur at the same rate on Earth. Microgravity may also affect drug metabolism. Medications that work normally on Earth may work differently in space, with altered absorption rates and elimination rates. Mars's 38% gravity adds yet another layer of pharmacological uncertainty. Historians still argue over how much of Earth's pharmacological knowledge translates safely to Mars. Probably most, not all. Here is a related mainstream fact. Mental health is also a medical issue. On long missions, psychiatric emergencies can occur. Severe depression, anxiety disorders, psychotic breaks. All of these are documented in prolonged isolation contexts. The crew medic on a Mars mission must be prepared to handle mental health crises with limited tools. Psychotropic medications are part of the kit. Counselling and behavioural interventions are available. But the worst cases, a crew member experiencing a severe psychiatric break, are extremely difficult to handle safely in a small, isolated, life support dependent habitat. The risk is real. Historians still argue over whether such events are likely on Mars missions, but the possibility is part of every serious mission plan. A second light joke tonight. The phrase "I'm fine" will have very different weight on a Mars mission than it does on Earth. When someone on Earth says "I'm fine," it could mean any number of things. When someone on Mars says "I'm fine," the rest of the crew will be checking the telemetry. They will be reading their body language. They will be quietly monitoring how much they eat, how much they sleep, how much they laugh. Because on Mars, "I'm fine" might be covering something that could put the whole crew at risk. The crew will learn to hear each other very carefully. It is a strange kind of intimacy. Historians still argue whether medical emergencies alone would justify aborting a Mars mission early. Some mission plans include abort contingencies, but the physics is brutal. If an astronaut develops a serious medical problem mid-flight, the spacecraft cannot simply turn around and come back to Earth. The fuel is not there. The orbit does not allow it. The best option may be to continue to Mars and deal with the condition on the surface, or to attempt a free return trajectory that eventually swings back by Earth months later. Neither is ideal. The astronaut may die during the journey, or they may survive on Mars and then die there. Either way, the mission does not simply abort to a hospital. The fringe tidbit for tonight is that some mission planners have seriously considered whether a Mars crew should include a policy for euthanasia in the case of an untreatable terminal medical event. This is a genuinely grim consideration, but it is part of serious discussion because extreme situations may arise where a crew member is suffering with no hope of recovery and no way to return. What does the crew do? The answer's not easy. Some propose compassionate protocols. Others argue that every measure must be taken to preserve life. Neither position is universally accepted. It is an ethical problem without a clean solution, and it is one of many reasons why careful psychological selection of the first crew matters so much. Remember the appendicitis scenario, the blood clotting risks, the asynchronous telemedicine. Every medical event on Mars is orders of magnitude more serious than the same event on Earth, and these medical realities, combined with all the other factors we've already discussed, gradually shape a picture in which the first Mars astronauts face a journey that is much more likely to keep them on Mars than to bring them home. In the next section, we turn to the most humble and relentless enemy of all, Martian dust. Dust. Of all the enemies the first Mars astronauts will face, dust is the one that never sleeps. It is patient, it is fine, it is everywhere. It works its way into every mechanical joint, every seal, every filter, every lung. It is, on Mars, essentially a second atmosphere. And it is quietly, relentlessly trying to ruin everything. Let's understand Martian dust. It is the weathered product of billions of years of geological processing on a dry, mostly airless planet. The particles are extremely fine, on the order of 1 to 5 micrometers across, which is much smaller than most Earth dust. They are sharp-edged, not rounded by water erosion the way Earth dust is. Under the microscope, they look like tiny angular shards of rock. They are abrasive. They're charged electrostatically, they cling to everything. And then there is the chemistry. The regolith, the fine surface material, contains perchlorates in significant concentrations. Perchlorates are compounds that are mildly toxic to humans. They can interfere with thyroid function, cause respiratory irritation, and at higher doses cause more serious effects. Mars regolith also contains iron oxides, the rust that gives the planet its red colour, as well as silicates, sulfates, and various other mineral compounds. Some of these, when inhaled in fine particulate form, could cause lung damage similar to silicosis on Earth. Breathing Mars dust, without adequate filtration, is a long-term health hazard. Here is the mainstream fact. The first humans on Mars will track dust from the outside through the airlock into the habitat. Every spacesuit that comes in carries dust. Every tool that was used outdoors carries dust. Every boot has fine dust in its treads. Over weeks and months, even with rigorous cleaning protocols, dust accumulates inside the habitat. This is one of the main health concerns for long Mars surface stays. The habitat must have extensive filtration and cleaning systems. The astronauts must have careful protocols for removing and sealing suits, and they must accept that despite all of this, they will be breathing trace amounts of Martian dust year after year. Historians still argue over how serious the long-term health effects of Martian dust inhalation will actually be. Some researchers predict significant respiratory issues after years of chronic low-level exposure. Others argue that with good filtration and modest exposure, the risks are manageable. The uncertainty is large because we have, again, no direct experimental data. Everything is based on terrestrial analogues and chemical analyses of regolith samples from rovers and landers. The first crews will provide the first real health data, and those data may come with an asterisk. Light joke for tonight. Mars dust is essentially the clingy X of the solar system. You try to leave it behind, it follows you. You seal the airlock, it comes in anyway. You shower, it sticks to you. You scrub, it smiles politely at your effort. Days later, you find it in your hair. Weeks later, you find it in your lungs. Years later, you realize you are in some small percentage made of Mars now, which when you think about it is its own form of terraforming. The planet has just terraformed you, 1 micron at a time. The quirky, fringe tidbit tonight involves the Apollo astronauts' experience with lunar dust, which is a related but different problem. Apollo astronauts, after moonwalks, came back into the lunar module covered in lunar dust. They reported that the dust had a distinctive smell, often described as like burnt gunpowder, and that it irritated their eyes, noses and throats. Some astronauts developed what NASA later called lunar hay fever, which was a temporary allergic-like reaction to lunar dust. The dust also damaged equipment, wore out suit seals, and clogged mechanical systems faster than expected. Mars dust may be even worse because it is smaller, more chemically reactive, and more pervasive. Historians still argue whether the lunar dust experience fully prepares us for Mars dust, but it is a warning, not a precedent. Now layer in dust storms. Mars is famous for them. Regional dust storms can cover thousands of kilometers. Global dust storms can envelop the entire planet. They can last weeks. They can last months. During a global dust storm, visibility drops to essentially zero. Sunlight filtered through suspended dust becomes a faint orange glow. Solar panels, which are a primary power source for Mars missions, lose most of their output. Temperatures can shift. Atmospheric dynamics become unpredictable. The entire surface operation of a Mars base grinds to a halt until the storm passes. Here is the mainstream fact. Mars orbiters have documented global dust storms repeatedly. The 2018 global dust storm, for instance, ended the operational life of the Opportunity rover, which had been working on Mars for nearly 15 years, because it could not receive enough sunlight to recharge during the storm. Opportunity never woke up. A solar-powered Mars mission is vulnerable to dust storms in a way that nuclear-powered missions are not. Hence the emphasis, in modern mission planning, on nuclear power for crewed missions. A second light joke tonight. A global Mars dust storm is essentially the planet's version of telling you to take a very long involuntary vacation. You wanted to go outside? Not today. You wanted to do science? Maybe next week. You wanted to collect samples? Good idea, except you cannot see your hand in front of your helmet. The planet has decided politely that you are grounded until further notice, and you cannot negotiate with the planet. You just wait. Historians still argue over whether Mars dust will become less problematic with better engineering. Some optimists argue that future spacesuit designs and habitat filtration will solve the problem effectively. Others argue that dust is an irreducible feature of the Martian environment and that even the best engineering will only mitigate, not eliminate, the hazards. Experience suggests that both are partly right. Engineering will reduce dust problems. Dust will still be a problem. The balance will improve slowly over generations of Mars hardware. The fringe tidbit to carry into the night is that some biologists have speculated that long-term Mars colonists may eventually develop a slightly altered immune profile in response to chronic low-level dust exposure. Perhaps similar to how terrestrial populations living in particularly dusty environments sometimes develop altered respiratory responses over generations. Whether this adaptation would be genetic or merely developmental is uncertain. Whether it would matter for return to Earth is also uncertain. But dust over generations might become part of the biological signature of Mars humans. Remember the fine, sharp, perchlorate-laced dust. Every time you imagine the first humans on Mars, imagine the red stain they leave inside their habitat. Imagine their air filters, thick with accumulation. Imagine their suits, gradually degrading from abrasion. Imagine their lungs, carrying trace amounts of oxidized iron and silicate fragments. This is not dramatic in any single moment. It is just quiet, relentless, and cumulative. And it is one more reason why the first humans on Mars will not return. Their equipment and their bodies are slowly becoming Martian, micron by micron. Next, we look at the fragile miracle that is the Mars habitat itself. Let's step inside the habitat, the first Martian home. It is small. It is cozy in the way that submarines are cozy, efficient, carefully designed, a little claustrophobic. Every square meter has a function. Every surface holds equipment. The air tastes subtly of recycled plastic and machinery. The lighting, if the engineers did their jobs, mimics Earth's day-night cycle, though the windows, if there are any, show a landscape of rust and stone. Inside this habitat, 6 or so humans are surviving. Outside this habitat, they would not survive for more than a minute or two. The habitat is, in the most literal sense, the only thing standing between them and a planet that does not want them alive. Here is the basic problem. Mars has essentially no breathable atmosphere. The surface pressure is about 6 millibars, compared to Earth's 1,013 millibars at sea level. That is roughly 0.6% of Earth's pressure. It is almost a vacuum. The atmosphere is 95% carbon dioxide, with traces of nitrogen, argon and other gases. There is essentially no oxygen. Temperatures can swing from about minus 140 degrees Celsius at night near the poles to about 20 degrees Celsius on a sunny equatorial afternoon. The median temperature is around minus 60 degrees Celsius. a human without a suit would, within seconds, experience catastrophic decompression, freezing, and suffocation. The habitat and the suits are the only things that keep this from being the default experience. Here is the mainstream fact. A Mars habitat is a life support system wrapped in a shelter. It must continuously provide breathable air, potable water, edible food, comfortable temperature, adequate humidity, and protection from radiation and dust. It must handle waste, human, mechanical, biological. It must generate power. It must recycle as much as possible, because resupply is months away. It must be repairable with the tools and spare parts on hand. It must essentially be a small, reliable, closed-loop biosphere with enough redundancy to keep functioning even when things break. Now the uncomfortable truth. Things break. Mechanical systems wear out. Filters clog. Pumps seize. Valves leak. Computers glitch. Wiring degrades. Seals weaken. Every single subsystem of a Mars habitat has some failure mode. In the best case, failures are minor, predictable, and fixable with spare parts. In the worst case, failures cascade. A single bad sensor can bring down an air system. A single bad weld can pop a pressure seal. A single bad day for a single piece of hardware can kill the whole crew. Historians still argue over the proper redundancy levels for Mars habitats. Too little redundancy, and the crew is at high risk of fatal failures. Too much redundancy, and the habitat becomes too massive to land and support. The balance is a compromise. Serious designs typically involve multiple independent life support loops, independent air recycling systems, independent water recycling systems, independent power sources, so that a failure in one loop does not kill the crew. But even with redundancy, operating a Mars habitat for 3 years with only the hardware you brought is a monumental test of engineering. Light joke for tonight. A Mars habitat is essentially the world's most high-stakes IKEA assembly project, with the additional feature that if you misread the instructions, you and your colleagues will die in the cold, oxygen-free dark. Also, half the parts are labelled only in acronyms, and the screwdriver you need is missing because you used it last week to fix the toilet, and also you need to fix the toilet. It is not a calming thought, but it is the reality of keeping a habitat running. Here is the quirky, fringe tidbit. One of the most important components of any Mars habitat is, weirdly, the toilet. Waste management in microgravity is already a solved-ish problem on the ISS, but on Mars, with reduced gravity and long-duration use, it remains tricky. Human waste must be managed in a way that does not contaminate the habitat, does not waste precious water, and, in the long run, could potentially even be used for agriculture. Early Mars missions will probably bag and store solid waste, while liquid waste may be recycled directly through urine-to-water processes. Some ISS technology does this routinely. The phrase, "yesterday's coffee is today's coffee," is a real joke astronauts tell about the ISS water recovery system, and it will be even more literal on Mars. A mainstream fact about Mars habitats is that they need significant power. Life support, lighting, computing, communications, heating, and any scientific equipment all require electricity. Solar power works on Mars but is vulnerable to dust storms and requires large panel arrays. Nuclear power, in the form of small fission reactors, is the preferred option for many crewed mission concepts. The kilopower reactor, developed by NASA and tested in 2018, is a small nuclear reactor designed to produce about 10 kilowatts of power for long-duration missions on the Moon or Mars. A full-scale kilopower class system, or several of them, might power a Mars habitat for a decade or more, safely, even during dust storms. Without reliable power, the habitat cannot function. Power is life. Historians still argue over whether the first crewed Mars mission should rely on solar power, nuclear power, or a hybrid. Each has trade-offs. Solar is lightweight but vulnerable. Nuclear is heavy and politically controversial but reliable. Most serious current proposals favour nuclear with solar as a backup, but the final architecture of the first missions may look different depending on politics and engineering readiness. Second light joke tonight. A Mars habitat is essentially the most expensive one-bedroom rental you will ever live in. The rent is paid in risk, effort, and the possibility of not coming back. The amenities include recycled water, limited lighting, a small garden of potato plants, a view of a red desert, and 6 roommates you cannot kick out. Utilities are included, but the utility bill is your life. The rental agreement is signed in blood, metaphorically. Tenant reviews are mixed. Here is another mainstream fact. Food is a significant challenge. The first Mars crews will bring substantial food supplies from Earth, but they will also be expected to grow some food on Mars in enclosed greenhouse modules. Experiments on the ISS have already demonstrated successful growth of various leafy greens and some other crops in microgravity. Mars gravity, being somewhat higher, should actually make plant growing easier than ISS growth, though still different from Earth. Potatoes in particular are often highlighted as a good candidate Mars crop because they are calorie-dense, relatively hardy, and can be grown in enclosed volumes. The movie The Martian famously dramatised potato farming on Mars. The real science is less dramatic but broadly consistent. The first Mars crews will probably grow a portion of their food, particularly fresh vegetables, but they will still depend heavily on packaged food for the bulk of their calories. The fringe tidbit to tuck into the night is that some colony architects have envisioned, on longer timescales, full closed-loop agricultural systems in which all waste is recycled into plants and all food is grown on Mars. Such systems, called Controlled Ecological Life Support Systems or CELSS, have been researched for decades. They have not yet been fully demonstrated on any real mission. A fully closed loop requires mastery of dozens of cycles: water, carbon, nitrogen, phosphorus, trace elements, all of them running continuously and in balance. Mars colonies will probably start with partial closure and gradually move toward greater closure over decades. Full closure is a long-term goal, not a first mission feature. Remember the habitat's fragile miracle. It is a small, highly engineered shelter keeping the crew alive in a hostile environment. Every mechanical failure is a test. Every resupply mission is a lifeline. And the crew's ability to maintain their home over years is one of the least discussed but most important determinants of whether they return. Next, we turn to the politics and priorities of Earth, which can change suddenly while the crew is gone. Now we turn to a reason for one-way Mars travel that has nothing to do with physics or biology. It has to do with politics, with funding, with the shifting priorities of governments and corporations, with the fact that the Earth you left and the Earth you hope to return to may have quietly changed the rules during the 2 to 3 years you were gone. Here is the basic dynamic. A crewed Mars mission is astronomically expensive. The most optimistic cost estimates put the total program at tens of billions of dollars. More realistic estimates put it in the hundreds of billions. The funding has to come from somewhere. Historically, large space programs have been funded by national governments, often during periods of geopolitical competition or prestige-seeking. The Apollo program, which cost about $25 billion in 1960s money, equivalent to something like $200 billion today, was fueled by the Cold War space race. When the Cold War ended, interest in further crewed lunar exploration waned. Funding dropped, missions were cancelled, astronauts who had trained for future flights retired without ever flying. A Mars program faces the same risks, but spread over a longer time. A crewed Mars mission from first launch to crew return might take 3 to 4 years. Over that time, elections happen, governments change, economies shift, priorities change. A program enthusiastically funded in year 1 might face budget cuts in year 2, cancellation threats in year 3. The return vehicle, which needs funding and delivery to arrive at the right time, might be delayed or defunded. The astronauts sitting on Mars might receive a polite delayed message explaining that the ride home is no longer on schedule. Here is the mainstream fact. The Apollo program was dramatically cut short after Apollo 17 in 1972. Planned Apollo missions 18 through 20 were cancelled, and the hardware was repurposed or mothballed. Astronauts who had trained for those missions never flew to the moon. The cancellations were driven by budget pressures, the Vietnam War, and shifting national priorities. The Mars missions of the future face similar risks. A program that survives one administration may not survive the next. A program that survives peace may not survive war. A program that survives economic prosperity may not survive recession. Historians still argue whether Apollo's cancellation was a mistake or a sensible reallocation of resources, but either way, it happened, and space advocates are still recovering from it. Light joke for tonight. A Mars astronaut's return ticket is essentially the world's most committed political promise, which means it is, historically, one of the most reliably broken categories of promise. "We will bring them home" is a phrase that sounds good in a press release and terrible in a budget hearing. The astronauts, already on Mars, can only hope that enough politicians keep their word. Their lives depend on it, and yet they have no vote in the matter. It is a peculiarly helpless position. The quirky fringe tidbit is that some space advocates have proposed that crewed Mars missions should be structured to minimize political risk. For example, multiple international partners, not just one country, should participate, so that the cancellation of funding by any single nation does not kill the whole mission. Some argue for privatizing key elements of the mission on the theory that corporate commitments may be more durable than political ones. Others argue that only a very ambitious, inspiring mission can sustain the political will to succeed. Historians still argue over which model is likely to produce the first successful crewed Mars mission. All models have historical precedents and failure modes. None is obviously right. Here's another mainstream fact. Many Mars mission concepts include ambitious plans for return that depend on multiple subsequent launches. For instance, one common plan is to send the Earth return vehicle, the MAV, plus possibly a separate trans-Earth injection stage, in an earlier launch window before the crew arrives. Then send the crew later, knowing that their return vehicle is already in place on Mars, fueled and waiting. This architecture has the advantage of reducing risk, but it has the disadvantage of requiring multiple successful launches across multiple launch windows, all funded and executed over many years. If any of those launches fail, or if political will falters, the crew may arrive on Mars without a functioning return vehicle. At that point, they are, in a very concrete sense, stranded, awaiting a subsequent rescue that may or may not come. Second light joke tonight. Mars mission planning is essentially a form of trust exercise with the future. You on Mars must trust that Earth will still be willing to launch your return vehicle on time. You must trust that the infrastructure will be maintained. You must trust that elections will go your way. You must trust that economies will not collapse. You must trust that pandemics will not divert attention. You must trust that war will not redirect resources. Trust in this context is both a lovely virtue and a worrying strategy, and yet every Mars astronaut signs up for it. Historians still argue over whether the first Mars missions will succeed before political will fails. Some argue that a rapid, well-funded first mission, executed within a single political cycle, is the safest path. Others argue that slow, steady infrastructure building missions are more robust because they build capability gradually. The debate has no clear winner. Different space agencies are pursuing different models, some faster, some slower, some more international, some more unilateral. Here is another mainstream fact. Even if political funding remains reliable throughout a mission, other forms of political risk can disrupt operations. Mission control, for example, typically involves hundreds of engineers across multiple facilities. Strikes, organizational restructuring, contractor disputes, security incidents, cybersecurity attacks, and many other events could temporarily disrupt mission support. On most Earth-based projects, such disruptions are absorbed with minor delays. On a Mars mission, even a few hours of support downtime could have serious consequences for the crew. The fringe tidbit to carry into the night is that some analysts have seriously considered the question of what happens if Earth experiences a major civilizational disruption. A pandemic, a world war, an asteroid strike, a collapse of global trade, while the Mars crew is gone. If the Earth the crew left is no longer functionally able to support a Mars return mission, what then? The answer is grim. The crew stays on Mars indefinitely with whatever resources they have on hand. If they cannot resupply, they eventually die. If they can grow enough food and maintain enough equipment to survive for decades, they might. A cut-off colony, abandoned by an Earth that has its own problems, is a staple of science fiction. It is not yet a real scenario, but it is not a crazy one either. Historians still argue over how likely such scenarios are in any given century, but risk analysts take them seriously. Remember that the return is not just a physics problem, it is also a political one. It depends on decisions made by people on Earth, months and years in advance, in conditions the crew cannot influence. And political decisions, as history shows, are unreliable. Next, we look at the simple, cold mathematics of how much it costs to bring the first crew home. Money. Let's talk about money. Because every one of the physics problems and biology problems and politics problems we have discussed so far is, in the end, also a money problem. Every shielding design, every medical kit, every return vehicle, every backup system, every kilogram of fuel, all of it costs something, and the total cost of bringing a crew home from Mars is, in most serious analyses, so high that at some point the cost-benefit analysis starts to tilt. Not in favour of rescue, in favour of letting the astronauts stay, building more infrastructure, and using the money to send the next crew instead. This sounds brutal. It is, in a sense, brutal, but it is also how large engineering programs actually make decisions. And the first crewed Mars mission will be, among other things, an exercise in triage. Here is the basic math. Sending a mission to Mars, the first mission, with no existing infrastructure, is enormously expensive. Every kilogram of payload that reaches the Mars surface costs on the order of hundreds of thousands to millions of dollars, depending on the launch vehicle and the mission architecture. A full crewed mission, including habitat, supplies, life support, propellant and hardware, might require 100 to several hundred tons of mass on the Mars surface, plus additional mass in Mars orbit for the return vehicle. Even at a cost of $1 million per kilogram delivered to Mars, an aggressive target currently considered optimistic, the mission costs quickly reach tens of billions of dollars. The return segment specifically adds enormous cost. A Mars ascent vehicle, an Earth return vehicle, the fuel for both, the navigation systems, the re-entry hardware, the life support for the return journey. All of it must be funded, built and delivered. Much of it must be in place before the crew even arrives. Building all that capability for the first mission essentially doubles the cost compared to a one-way mission of the same crew size. Some estimates put the return portion of the mission at 30 to 50% of the total mission cost. Here is the mainstream fact. Many space engineers and economists have argued that the cheapest, fastest way to establish a human presence on Mars is to commit to one-way missions at the start and save the return mission infrastructure for later missions once Mars has built up enough in situ capability. The idea is that a first one-way mission is cheaper, quicker, and more likely to succeed. Once established, the colony can expand, build infrastructure, and eventually support return missions as a secondary capability. The astronauts of the first mission serve as permanent colonists. The astronauts of later missions may be able to return if return missions become affordable. Historians still argue over whether this is ethical. Some argue that sending humans on a permanent one-way journey without the option of return violates the principle of informed consent because the psychological and biological consequences are too uncertain. Others argue that fully informed volunteers can make this choice, and that the scientific and civilizational benefits justify the trade-offs. The Mars One project, which was a private initiative in the 2000s to send one-way colonists to Mars, explicitly advertised itself as a permanent one-way journey. The project received huge numbers of volunteers, but ultimately failed to raise funding and went bankrupt in 2019. The concept, however, lives on in various forms. Light joke for tonight. Mars colonization is essentially the world's most extreme Kickstarter campaign. The rewards tier for a $10 billion contribution is, "We name an airlock after you." The rewards tier for a $100 billion contribution is, "We send a tiny robot to put a photo of your dog on a Martian rock." The rewards tier for a $1 trillion contribution is, "A human being survives a round trip." The economics are, shall we say, demanding. The quirky fringe tidbit is that some entrepreneurs have proposed that private sector involvement can dramatically reduce Mars mission costs. SpaceX, founded by Elon Musk, has been publicly focused on Mars colonization for years, with the Starship vehicle specifically designed to support large-scale Mars travel. The company has proposed mission architectures that are much cheaper than traditional government approaches, partly by using fully reusable vehicles, partly by using in situ fuel production, partly by accepting higher risk. Historians still argue over whether these projections are realistic or overly optimistic. The first actual crewed Starship Mars missions, if they happen, will provide real data. Until then, the cost estimates are contested. Here is another mainstream fact. The cost of keeping existing Mars infrastructure in operation is much lower than the cost of building new infrastructure. Once a habitat is on Mars, maintaining it is relatively cheap. Life support, food, minor repairs. Bringing people to it, and to some extent keeping them supplied, is moderately expensive. Bringing them back is the expensive part, so the long-term economics favour permanence. Each person who stays on Mars reduces the average cost per person of the colonization effort. Each person who insists on returning raises the average cost. Second light joke tonight. A Mars mission budget spreadsheet essentially has a line item called returning the crew that costs as much as the rest of the mission combined. Every finance officer looks at that line and says, "You know, if we just removed this line, we could afford another crew and a larger habitat." And every mission planner says, "Yes, we know, but people might notice." And the conversation becomes awkward. Over time, over multiple missions, the compromise often becomes, the first few crews stay permanently and return becomes an affordable option only after the colony is self-sustaining. Historians still argue over whether a permanent Mars colony is ever likely to be self-sustaining. Some argue that given enough decades and enough infrastructure investment, Mars can eventually support its own life support chain, food production, and manufacturing, reducing dependence on Earth. Others argue that a true closed-loop Mars economy is centuries away, if it is possible at all. Either way, the first crews will not be self-sustaining. They will depend on Earth for essentially everything except what they can extract from the Martian environment directly, and their survival will depend on the continued willingness of Earth to pay their bills. The fringe tidbit tonight is that some long-term Mars colonization economists have proposed that the colony should be designed explicitly as a one-way permanent settlement from the start, rather than trying to hybridize with a return mission architecture. This approach would save money, reduce complexity, and force the mission to focus on sustainable long-term habitation rather than brief, showy visits. It is a surprisingly persuasive argument when you look at the numbers. It is also a deeply uncomfortable argument for many people who imagine Mars missions as adventures from which heroes return. The tension between these two visions, heroic return versus permanent colony, shapes much of the actual Mars mission planning that happens behind closed doors. Remember that money makes the decision. Physics says return is hard. Biology says return is hard. Politics says return is hard. Money says return is the most expensive hard thing. And when you stack all the hards together, what you get is a conclusion that everyone nods at reluctantly in serious planning meetings. The first humans on Mars are staying. Next, we look at how, over time, the Mars colonists will drift culturally from Earth. Time passes differently when you're on another planet. Not in the Einsteinian sense, though minutely, yes, the different gravitational potential does slow or speed time, but at negligible rates. But in the cultural sense, Earth keeps evolving. Language shifts, slang updates, new movies, books, music, memes, references, political movements, technological trends, and fashion choices all continue to roll across Earth's surface at a pace that has no reason to slow down just because 6 humans have moved to Mars. And those 6 humans, isolated by time delay and physical distance, will increasingly live in a different cultural space. Here is the mainstream fact. Cultural drift has been observed in all known cases of isolated human communities. Small groups of humans who are separated from a larger population for extended periods inevitably develop distinct dialects, customs, and norms. This is true for Polynesian island populations, for rural Appalachian communities, for Amish settlements, for Antarctic research crews, for submarine crews, for remote mining towns. The patterns are consistent. Small isolated groups diverge, linguistically and culturally, from their parent populations, often faster than outside observers expect. Now consider Mars colonists. They're not physically distant by hundreds of kilometers or a few days of travel. They're physically distant by hundreds of millions of kilometers and months of travel and an asynchronous communication delay. Their isolation is more extreme than almost any previous human communities. Their cultural drift over years and decades should be equally extreme. Historians still argue over how quickly cultural drift will become noticeable in a Mars colony. Some argue that modern communication technology, including recorded videos, podcasts, email, social media posts, will keep Mars culturally aligned with Earth despite the delays. Others argue that the lived experience of Mars will be so different from Earth that cultural divergence will be inevitable, even rapid. The first generation of Mars colonists, the original crew, plus any who join in subsequent missions, will be culturally Earth people living on Mars. The second generation, born on Mars, will be culturally Mars people, with Earth as a distant inherited heritage. By the third generation, Mars culture will be firmly its own thing. Here is a specific example. Language. On Mars, the crew will live in a tightly constrained environment, where certain words become much more important than they are on Earth. Airlock, suit check, filter, leak rate, EVA, dust protocol. These will be part of daily vocabulary. Earthlings rarely say airlock in ordinary conversation. Mars colonists will. Over time, these specialized terms will develop nicknames, slang variants, compressions. New verbs will emerge. Dusting in might become a verb meaning entering the habitat from outside and going through cleaning protocols. Filter day might become a regular weekly event. The language will subtly drift. Over decades, if the colony grows, the drift will become noticeable. Earthlings visiting the colony will notice vocabulary they don't recognize. Mars colonists will notice Earth slang that feels outdated to them because it is slang they learned years ago and Earth has moved on. Light joke for tonight. Mars colonists will essentially be the world's most specialized vocabulary club. They will have dozens of technical words that Earthlings will not understand, because Earth does not have atmospheric pressure issues in their homes. They will use those words without thinking, and when they try to explain their lives to Earth relatives, they will find themselves constantly defining terms. What do you mean, dusted in? Oh, I mean I came inside and cleaned off. Yes, every time. Yes, it takes 20 minutes. Yes, it is annoying. Yes, we have a word for it. The quirky fringe tidbit is that some anthropologists have proposed that long-term Mars colonies may eventually develop distinct religions, philosophies, and social structures specific to Mars life. The Martian environment will shape worldview in subtle ways. The experience of being outside in a suit, seeing the thin pale sky, feeling the light gravity, knowing that the planet actively kills without protection. All of this may foster philosophical attitudes quite different from those of Earth people who live in a mostly forgiving environment. Some Mars colonists may develop new religions that emphasize human ingenuity, collective survival, or the cosmic significance of interplanetary life. Others may deepen their engagement with existing Earth traditions. Historians still argue whether these new cultural forms will emerge spontaneously or will require conscious cultivation, but most agree that something like cultural differentiation will happen, given time. Here is another mainstream fact. Legal systems will also diverge. A Mars colony will eventually need its own laws, its own governance, its own courts. Earth law, designed for Earth conditions, does not always translate smoothly to Mars. Questions like property rights, reproductive rights, criminal justice, dispute resolution, labour practices, and political representation all need to be worked out for Mars specifically. Early colonies may rely on national laws of the colonists' home countries, or on international frameworks like the Outer Space Treaty of 1967, which declares that no country can claim sovereignty over celestial bodies. But as colonies grow, local governance will emerge. Whether Mars becomes a formal political entity, or a loose federation of national outposts, or something entirely new, will depend on choices made over decades. Second light joke tonight. A Mars colony is essentially a startup country, with the difficulty of starting a country multiplied by the difficulty of breathing. The founders are building not just a business or a community, but a whole new society from scratch, on a planet that does not come with existing infrastructure. Every decision, how to allocate resources, how to resolve disputes, how to educate children, how to bury the dead, has to be made, often under pressure, often without precedent. It is, in a way, a new frontier in exactly the way Earth frontiers used to be, except the frontier is hostile in a new set of ways. Historians still argue over which Earth historical precedents are most relevant to Mars colonization. The American colonies of the 1600s, the Australian colonies of the 1700s, the Antarctic research stations of the 1900s, the space station cooperatives of the 2000s. Each comparison captures some features and misses others. Mars colonies will probably be unlike any of these, because the scale of isolation, the technological complexity, and the reduced gravity environment are all unprecedented. A new kind of human community, with new patterns, will emerge if Mars colonization succeeds over generations. The fringe tidbit tonight is that some futurists have suggested that Mars colonies may eventually develop distinct forms of art that Earth does not have. Martian poetry might emphasize different themes: the color of the sky, the sound of the wind through the thin atmosphere, the smell of recycled air. Martian music might use new rhythms or tonalities. Martian visual art might incorporate regolith, ice, and the specific colors of Mars's surface. These forms, developed over generations, would become part of Martian cultural identity. Earth people would study them with interest. Mars people would live them. Remember the slow drift. Language changes, law changes, art changes, religion changes, family structures change, holidays change. Everything changes slowly over generations as a colony develops its own life. And this means that even if the first humans on Mars could eventually return to Earth, they would return to a place that is no longer quite theirs, because they themselves are no longer quite Earth people. The first humans on Mars become, gradually, the first of a new cultural lineage. Going home for them stops being a simple geographical question and becomes an identity question, and many of them, if asked, may choose to stay. Next, we place them in the context of historical voyagers who made similar choices. Let's drift back in time for a softer perspective, because the first humans on Mars are not the first humans to face a one-way journey. They are not the first to leave everything familiar, cross a dangerous medium, and arrive somewhere permanent. The pattern is old, very old. It runs through human history like a thread, and looking at it might help you make sense of what the Mars astronauts are really choosing. Start with the Polynesian navigators. Over roughly 2,000 years, beginning around 1500 BCE, skilled ocean-going peoples spread across the vast Pacific. They travelled in double-hulled canoes equipped for long voyages. They navigated by the stars, by the patterns of ocean swells, by the flight paths of birds, by the subtle clues of distant land, cloud formations, changes in water colour, floating debris. They sailed from island to island, sometimes across open ocean for thousands of kilometres, settling in places like Hawaii, Easter Island, New Zealand, and many small atolls between. Here is the mainstream fact. Some of these voyages were definitely one way. A canoe that set sail from Tahiti for Hawaii, for example, faced a journey of several thousand kilometres across open ocean. Once they arrived in Hawaii, some groups could, in principle, attempt a return voyage. Others settled permanently and did not return. The Easter Island settlers, who arrived on one of the most isolated inhabited places on Earth, eventually lost the ability to make open ocean voyages altogether because the island's resources could not support the forest-based canoe industry needed. They became, in a very real sense, marooned by their own settlement. Historians still argue whether this isolation was a choice or a consequence of resource constraints, but either way, it happened. The Polynesian voyagers faced in many ways challenges similar to those of Mars astronauts. Unknown destinations, no rescue, limited supplies, complete dependence on crew skills, navigation by physics, the stars, the ocean, the wind. The reward was a new home. The cost was for many never returning to the homeland. Light joke for tonight. Polynesian navigators are essentially the prehistoric version of astronauts. They sailed into the unknown using nothing but stars, skill, and nerve. They carried food, water, and small cuttings of plants for replanting on new islands. They did not have backup rescue ships. They did not have GPS. They did not have radios. They had, at most, maybe a few oral instructions from older navigators, and they found their destinations, and they settled them, and many never came back. The first Mars astronauts are their cosmic descendants, carrying slightly more technology and slightly less sunscreen. The quirky, fringe tidbit is that recent archaeological and genetic evidence suggests that Polynesian navigators may have reached South America, or that South Americans may have reached Polynesia at some point before European contact. Sweet potatoes, which are native to South America, appear in Polynesian archaeological sites from before any known European contact with the Pacific. This is one of the most intriguing open questions in Pacific prehistory. Historians still argue over exactly how and when this contact happened, but the basic evidence is hard to explain without assuming that someone at some point sailed a very long way and returned, or that two groups met in the middle. The fact that this is still an open question thousands of years later is a reminder that the cultural records of one-way voyagers are often patchy and debated. Now consider the Mayflower voyagers of 1620, a group of English religious dissenters known to history as the Pilgrims sailed across the Atlantic Ocean to establish a colony in what is now Massachusetts. The voyage took about 2 months in a wooden ship. The destination was uncertain, the supplies limited. The first winter killed nearly half of them, and importantly, most of the surviving pilgrims never returned to England. They built a colony. They had children. Their children had children, and their descendants are still in New England today, generations later. The Mayflower voyage is remembered as a founding journey, a story of immigration and permanence, not as a round-trip expedition. Here is another mainstream fact. Throughout human history, most long-distance migration has been one way. People left one place and went to another. The idea of returning home after a major migration is, historically, unusual. The Aztec ancestors who migrated from the American Southwest to central Mexico did not return. The Bantu peoples who migrated across sub-Saharan Africa over centuries did not return. The Anglo-Saxons who migrated from northern Germany to Britain did not return. The Vikings who settled Iceland did not mostly return to Scandinavia. The European immigrants who came to the Americas in the 1800s and 1900s often did not return to Europe. Migration is, in its most common form, permanent. Return migration is a specific, less common pattern. Historians still argue over why return migration is less common than one-way migration, but several factors are consistent across cases. The cost of return is often high. The new place has new opportunities, new families, new commitments. The old place has often changed in ways that make return unappealing. Identity shifts. After years in the new place, people no longer feel fully at home in the old place. All these factors, combined, favour permanence. Mars, in this sense, fits squarely within a long human pattern. It is just more extreme. Second light joke tonight. Mars astronauts are essentially the latest chapter in a very old book about humans who packed up and left. The book is called Why We Moved, and it has been running new editions for about 300,000 years. Most chapters end with the protagonist settled in the new place, building a life, becoming something slightly new. The Mars chapter will be just another in this long series. The difference is that Mars is for now inhospitable in ways that no Earth destination has been. But humans have adapted to inhospitable places before: the Arctic, the deep jungle, the Himalayan highlands, the central deserts. Mars is just the next one. Here is another interesting historical parallel. The early Antarctic expeditions of the early 1900s were, effectively, long-duration isolation missions with significant risk of not returning. Some expeditions succeeded. Some, like the Scott expedition of 1912, ended with the death of all members before they could return to the coast. The expedition journals, found later, tell stories of hope, struggle, exhaustion, and final acceptance. The bodies were eventually recovered and memorialized. The stories became part of exploration mythology. Mars astronauts who die on Mars, which some will statistically, will become similar figures. explorers who gave their lives to the effort, commemorated but not recovered. Their graves, if graves are made, will be on another planet. The fringe tidbit to tuck into the night is that some space historians have argued that the Mars colonization narrative is essentially identical, structurally, to the American colonization narrative of the 1600s through 1800s. Both involve crossing a hostile medium to reach a distant land. Both involve extreme hardship in the early years. Both involve gradual population build-up and eventual cultural differentiation from the parent society. Both involve one-way migration for most participants. Both involve the creation of new identities and new political structures. The main differences are scale, technology, and environmental conditions. The structural similarity is striking. Historians still argue whether this parallel is useful or misleading, but it is certainly thought-provoking. Remember the voyagers, the Polynesians crossing the Pacific, the Pilgrims crossing the Atlantic, the Anglo-Saxons crossing the North Sea, the Vikings settling Iceland, the Antarctic explorers, the generations of immigrants who sailed or walked to new lives. They are the ancestors spiritually of the first Mars astronauts. The first Mars astronauts are joining a long tradition, and in that tradition, most travellers did not go home. They built new homes. They became new peoples. Next, we close the circle with the final section and ease you into the soft wind down. Now, with the red dust outside and the habitat humming gently around you, let's gather the threads together. Over 19 sections, you have met the many reasons why the first humans on Mars will not come back. The distance, so vast it breaks ordinary comparisons. The launch windows, so narrow they dictate entire mission schedules. The rocket equation, so brutal that returning fuel almost breaks the math. The ISRU plant, elegant and fragile. The radiation quietly accumulating. The bones forgetting gravity. The bodies slowly rearranging. The hearts rounding. The Mars-born children, fundamentally adapted to a lighter world. The long silence. The delayed conversations. The unrescuable medical emergencies. The dust that wants you dead. The fragile miracle of the habitat. The shifting politics. The cold mathematics of rescue. The quiet cultural drift. The ancient human pattern of one-way voyages. Each of these, on its own, is a nudge, not a wall. Each of these, stacked with the others, becomes a soft, firm, unmistakable current. The current flows in one direction. It flows away from Earth. It flows towards staying. And the first humans on Mars, without fighting it, without dramatically arguing about it, will mostly, gently, go where the current takes them. They will stay. You probably knew this, somewhere in your sleepy mind from the very first section tonight. You knew it when the colonists stepped onto the dust and looked back at the ship. You knew it when the distance was laid out as 225 million kilometers. You knew it when the bones started losing mass, the heart started changing shape, the political will started wavering. Every part of the story was telling you the same thing, in different voices. Mars is not a destination. Mars is a destination that becomes a departure point for a new chapter of human history. And now, the real thing to hold as you drift off. The first humans on Mars are not going to be tragic figures. They are not going to be failed travellers who could not find their way home. They're going to be founders. They're going to be in the fullest sense the first of something. The first to live, work, struggle, love, create, and eventually die on another world. The first whose children were born outside Earth. The first whose graves were dug in rusty soil. The first to look at Earth as a bright distant star, not as a home they could return to, but as a place they came from, a place they remember, a place that remembers them. Their story will not be one of failure, but of extension. The human story extends to Mars, and it does not need to curve back to Earth to count. That is the strange, beautiful dignity of being a one-way traveller. You accept that your life is now in a new place. You accept that the place is hard. You accept that you will be remade by it, and you accept that this is not only okay, but good. Because in being remade, you become part of something that has never existed before. A Mars person, a founder, a first. And now let's slow down. Let's really slow down, because you're getting very sleepy, and this is the wind down, and there is no need to rush toward the end. Close your eyes if they aren't closed already. Let your breath settle. The room around you is quiet. The world outside is turning without you as it always does. Tomorrow will come, and you will be in it, and that is a very ordinary, very beautiful thing. Somewhere, if not tonight, then someday soon, a small crew will lift off from Earth toward Mars. They will ride a rocket bigger than any we have used before. They will spend months in a silver tube floating through the dark. They will arrive. They will step down onto the dust. They will look back at the ship, and they will begin a story that we, on our soft pillows on a blue planet, cannot fully imagine. They will eat dinner. They will fix equipment. They will call home with long delays. They will look at the pale sun. They will grow plants. They will take care of each other, because there is no one else to take care of them. They will get old there. Some will die there. Some will have children. Those children will grow up under a rust-coloured sky, and they will think it is normal because it is theirs. You do not need to worry about them tonight. They do not need your worry. They will do what they do, and they will be okay in the particular way that one-way travellers have always been okay. Not perfectly, not without loss, but in their own stride, making their own home out of whatever is there. You, though, are right here, on Earth, in your bed, with the fan humming softly, with gravity holding you exactly as you're used to being held, with air that you can breathe without equipment, with a sky that will be blue tomorrow morning whether you remember it or not. You are, in this specific way, deeply and quietly lucky. The first Mars colonists would, in a sense, envy the smallness and warmth of this moment you're living in. A bed, a blanket, a breath, an Earth sky. Tomorrow. Rest now. Let the numbers fade. Let the rocket equations blur. Let the launch windows slip past. Let the habitats hum softly into the background. Let the Mars dust settle in some faraway crater. You don't have to solve the Mars problem. You don't have to bring anyone home. You don't have to know whether the first humans on Mars will be happy or not. They will make their choices. You are making yours. And your choice right now is simply to rest. Sleep well. The first Mars colonists are tonight just an idea of people who will someday leave and who will make a new home and who will not come back. They don't need you tonight. They have their own mission. Yours is smaller, softer, and closer. Yours is the blanket, the breath, the quiet hum of a planet that has been your home your whole life. A planet that will still be here in the morning. Close your eyes one more time. Let go of the whole long story. Let go of Mars. Let go of the distance, the launch windows, the rocket equations, the radiation, the bones, the hearts, the children, the silences, the delays, the dust, the habitats, the politics, the money, the culture, the history. Let it all drift softly away. You don't need any of it tonight. You only need this moment. You only need this breath. You only need this soft, warm, heavy, patient rest. The universe is very big, you're very small, and that tonight is the nicest thing in the world. Sleep well. The Martians, future and imagined, will do just fine without you.